Welcome to Course 2, the bits and bytes of computer networking. You might remember me from the lessons on the internet in the first course, but you also might have jumped ahead, in which case we are meeting for the first time. My name is Victor Escobedo, and I'm a corporate operations engineer. My passion for IT began way back when I was 9 years old and my dad brought home our first computer. He was a mechanical engineer and started using the computer to help him with his CAD work. This was the first time I was exposed to computers and later realized that you could install new software on it, including computer games. As I tinkered with the computer, surely to my dad's dismay, I became more and more interested in how it worked and eventually started to open up the case and peek inside. I found pieces that could be removed and even some that shouldn't, learning through trial and error along the way. I couldn't really explain what it was, but I just found the mechanics of how it all worked together so fascinating. Looking back, these were the seeds that inspired my career. But you see, where I grew up, going to college and pursuing a career wasn't exactly talked about or heavily encouraged. I'm a first-generation Mexican-American, and there weren't a lot of people I knew pursuing a career in tech. My friends and family were mostly worrying about graduating high school and making sure they had jobs, not really thinking about longer-term careers. My school didn't have the resources to offer many technical classes, and even though my father was working in mechanical engineering, computers were a tool to him, like a mill, ruler, or hammer. My parents encouraged me to work hard and pursue computers, but they couldn't really give me advice about college or a career in tech. To no real fault of their own, they just didn't have the experience necessary. When I decided to go to college, I decided to try my hand at computer science, since it could feed my curiosity for how computers worked at a more fundamental level. I realized that having this foundational knowledge really allowed me to understand some of the higher level concepts that were important in a career in IT. So while in school, I took my first job in IT for a small local company. I've been working in IT for 12 years now, with the last 7 years being here at Google. I now work on managing deployments of large internal IT projects for the company, applying the knowledge I've picked up over the years in my initial help desk role to make sure that I understand how I'm impacting our users and various support teams. In my role as a corporate operations engineer, I'm responsible for understanding the impact of changes on our corporate infrastructure. Because of this, networking skills are critical. I need to understand not just how applications work on a single system, but how they interact with all other systems in the company and even externally. So now that you know a bit about me, let's dig into the bits and bytes of networking. Computers communicate with each other a lot like how humans do. Take verbal communication as an example. Two people need to speak the same language and be able to hear each other to communicate effectively. If there are loud noises, one person might have to ask the other person to repeat themselves. If one person only somewhat understands an idea being explained to them, that person might ask for clarification. One person might address only one other person, or they may be speaking to a group. And there's usually a greeting and a way to close the conversation. The point is that humans follow a series of rules when they communicate, and computers have to do the same. This defined set of standards that computers must follow in order to communicate properly is called a protocol. Computer networking is the name we've given to the full scope of how computers communicate with each other. Networking involves ensuring that computers can hear each other, that they speak protocols other computers can understand, and that they repeat messages not fully delivered, just like how humans communicate. There are lots of models used to describe the different layers at play with computer networking, but for this course, we've selected the TCP/IP 5-layer model. We'll also be touching on the other primary network model, the OSI model, which has 7 layers. If you don't know what these models are or how they work, don't worry. We'll be deep diving into these topics throughout this course. It's super important to know these types of layered models to learn about computer networking because it's a really layered affair. The protocols at each layer carry the ones above them in order to get data from one place to the next. Think of the protocol used to get data from one end of a networking cable to the other. It's totally different from the protocol used to get data from one side of the planet to the other. But both of these protocols are required to work at the same time in order for things like the internet and business networks to work the way they do. Sometimes there are problems when computers on the internet or on these business networks try to communicate with each other, and often it's up to an IT support specialist to fix these problems. This is why understanding computer networking is so important. By the end of this course, you'll be able to explain all 5 layers of our model. Not only that, you'll be able to describe how computers determine where to send their messages and how network services like DNS and DHCP work. You'll also be able to use powerful tools to help you troubleshoot network issues. Are you ready? Let's dive in. To really understand networking, we need to understand all of the components involved. We're talking about everything from the cables that connect devices to each other to the protocols that these devices use to communicate. There are a bunch of models that help explain how network devices communicate, but in this course, we'll focus on a 5-layer model. By the end of this lesson, you'll be able to identify and describe each layer and what purpose it serves. Let's start at the bottom of our stack, where we have what's known as the physical layer. The physical layer is a lot like what it sounds. It represents the physical devices that interconnect computers. This includes the specifications for the networking cables and the connectors that join devices together, along with specifications describing how signals are sent over these connections. The second layer in our model is known as the data link layer. Some sources will call this layer the network interface or the network access layer. At this layer, we introduce our first protocols. While the physical layer is all about cabling, connectors, and sending signals, the data link layer is responsible for defining a common way of interpreting these signals so network devices can communicate. Lots of protocols exist at the data link layer, but the most common is known as Ethernet, although wireless technologies are becoming more and more popular. Beyond specifying physical layer attributes, the Ethernet standards also define a protocol responsible for getting data to nodes on the same network or link. The third layer, the network layer, is also sometimes called the internet layer. It's this layer that allows different networks to communicate with each other through devices known as routers. A collection of networks connected together through routers is an internetwork, the most famous of these being the internet. Hopefully you've heard of it. While the data link layer is responsible for getting data across a single link, the network layer is responsible for getting data delivered across a collection of networks. Think of when a device on your home network connects with a server on the internet. It's the network layer that helps get the data between these two locations. The most common protocol used at this layer is known as IP, or Internet Protocol. IP is the heart of the internet and most small networks around the world. Network software is usually divided into client and server categories, with the client application initiating a request for data and the server software answering the request across the network. A single node may be running multiple client or server applications. So you might run an email program and a web browser, both client applications, on your PC at the same time. And your email and web server might both run on the same server. Even so, emails end up in your email application and web pages end up in your web browser. That's because our next layer, the transport layer. While the network layer delivers data between two individual nodes, the transport layer sorts out which client and server programs are supposed to get that data. When you heard about our network layer protocol, IP, you may have thought of TCP/IP, which is a pretty common phrase. That's because the protocol most commonly used in the fourth layer, the transport layer, is known as TCP, or Transmission Control Protocol. While often said together as the phrase TCP/IP, to fully understand and troubleshoot networking issues, it's important to know that they're entirely different protocols serving different purposes. Other transport protocols also use IP to get around, including a protocol known as UDP, or User Datagram Protocol. The big difference between the two is that TCP provides mechanisms to ensure that data is reliably delivered, while UDP does not. Spoiler alert. We'll cover differences between the TCP and UDP transport protocols in more detail later. For now, it's important to know that the network layer, in our case IP, is responsible for getting data from one node to another. Also, remember that the transport layer, mostly TCP and UDP, is responsible for ensuring that data gets to the right applications running on those nodes. Last but not least, the fifth layer is known as the application layer. There are lots of different protocols at this layer, and as you might have guessed from the name, they're application specific. Protocols used to allow you to browse the web or send and receive email are some common ones. The protocols at play in the application layer will be most familiar to you, since they're ones you've probably interacted with directly before, even if you didn't realize it. You can think of layers like different aspects of a package being delivered. The physical layer is the delivery truck and the roads. The data link layer is how the delivery trucks get from one intersection to the next over and over. The network layer identifies which roads need to be taken to get from address A to address B. The transport layer ensures that the delivery driver knows how to knock on your door to tell you your package has arrived. And the application layer is the contents of the package itself.
Every computing device that we interact with on a day-to-day basis is a network device, right? Computers aren't standalone anymore in any way. From our phone to our tablet to our laptop to our desktops, they're all networked in some way. They're all talking to other computers. To a lot of people, networking is seen as some kind of black magic, and only certain people really understand what's going on. But in my experience, an IT support person who truly understands networking at a fundamental level is just able to perform every aspect of their job so much more successfully. There are a lot of networking courses available. This is actually something that people have been teaching in this manner, since the 90s. But I think this course is really different because it focuses on so many practical cases, as well as really focusing on the things that an IT support person needs to know and not necessarily a network engineer. We spend a lot of time on DNS. We spend a lot of time on different troubleshooting techniques and tools. We spend a lot of time just focusing on the kinds of things that on a day-to-day basis someone in IT actually needs to know about.
Lots of different cables and network devices can be used to allow computers to properly communicate with each other. By the end of this lesson, you'll be able to identify and describe various networking cables and networking devices. Computer networking is a huge part of the day-to-day role of many IT specialists, and knowing how to differentiate different network devices will be essential to your success. Let's start with the most basic component of a wired network: cables. Cables are what connect different devices to each other, allowing data to be transmitted over them. Most network cables used today can be split into two categories: copper and fiber. Copper cables are the most common form of networking cable. They're made up of multiple pairs of copper wires inside a plastic insulator. You may already know that computers communicate in binary, which people represent with ones and zeros. The sending device communicates binary data across these copper wires by changing the voltage between two ranges. The system at the receiving end is able to interpret these voltage changes as binary ones and zeros, which can then be translated into different forms of data. The most common forms of copper twisted pair cables used in networking are Cat5, Cat5e, and Cat6 cables. These are all shorthand ways of saying Category 5 or Category 6 cables. These categories have different physical characteristics, like the number of twists in the pair of copper wires that result in different usable lengths and transfer rates. Cat5 is older and has been mostly replaced by Cat5e and Cat6 cables. From the outside, they all look about the same, and even internally, they're very similar to the naked eye. The important thing to know is that differences in how the twisted pairs are arranged inside these cables can drastically alter how quickly data can be sent across them and how resistant these signals are to outside interference. Cat5e cables have mostly replaced those older Cat5 cables because their internals reduce crosstalk. Crosstalk is when an electrical pulse on one wire is accidentally detected on another wire, so the receiving end isn't able to understand the data, causing a network error. Higher level protocols have methods for detecting missing data and asking for the data a second time, but of course this takes up more time. The higher quality specifications of a Cat5e cable make it less likely that data needs to be retransmitted. That means on average you can expect more data to be transferred in the same amount of time. Cat6 cables follow an even more strict specification to avoid crosstalk, making those cables more expensive. Cat6 cables can transfer data faster and more reliably than Cat5e cables can, but because of their internal arrangement, they have a shorter maximum distance when used at higher speeds. The second primary form of networking cable is known as fiber, short for fiber optic cables. Fiber cables contain individual optical fibers, which are tiny tubes made out of glass about the width of a human hair. These tubes of glass can transport beams of light. Unlike copper, which uses electrical voltages, fiber cables use pulses of light to represent the ones and zeros of the underlying data. Fiber is even sometimes used specifically in environments where there's a lot of electromagnetic interference from outside sources, because this can impact data being sent across copper wires. Fiber cables can generally transport data quicker than copper cables can, but they're much more expensive and fragile. Fiber can also transport data over much longer distances than copper can without suffering potential data loss. Now you know a lot more about the pros and cons of fiber cables, but keep in mind, you'll be way more likely to run into fiber cables in computer data centers than you would in an office or at home. We're going to do a rundown of network devices in this video and the next one. Almost every IT specialist will have to interact with these sorts of devices on a regular basis. Cables allow you to form point-to-point networking connections. These are networks where only a single device at each end of the link exists. Not to knock point-to-point networking connections, but they're not super useful in a world with billions of computers. Luckily, there are network devices that allow for many computers to communicate with each other. The most simple of these devices is a hub. A hub is a physical layer device that allows for connections from many computers at once. All the devices connected to a hub will end up talking to all other devices at the same time. It's up to each system connected to the hub to determine if the incoming data was meant for them or to ignore it if it isn't. This causes a lot of noise on the network and creates what's called a collision domain. A collision domain is a network segment where only one device can communicate at a time. If multiple systems try sending data at the same time, the electrical pulses sent across the cable can interfere with each other. This causes these systems to have to wait for a quiet period before they try sending their data again. It really slows down network communications and is the primary reason hubs are fairly rare. They're mostly a historical artifact today. A much more common way of connecting many computers is with a more sophisticated device known as a network switch, originally known as a switching hub. A switch is very similar to a hub since you can connect many devices to it so they can communicate. The difference is that while a hub is a layer 1 or physical layer device, a switch is a layer 2 or data link device. This means that a switch can actually inspect the contents of the Ethernet protocol data being sent around the network, determine which system the data is intended for, and then only send that data to that one system. This reduces or even completely eliminates the size of collision domains on a network. If you guess that this will lead to fewer retransmissions and a higher overall throughput, you're right. Hubs and switches are the primary devices used to connect computers on a single network, usually referred to as a LAN, or local area network. But we often want to send or receive data to computers on other networks. This is where routers come into play. A router is a device that knows how to forward data between independent networks. While a hub is a layer 1 device and a switch is a layer 2 device, a router operates at layer 3, a network layer. Just like a switch can inspect Ethernet data to determine where to send things, a router can inspect IP data to determine where to send things. Routers store internal tables containing information about how to route traffic between lots of different networks all over the world. The most common type of router you'll see is one for a home network or a small office. These devices generally don't have very detailed routing tables. The purpose of these routers is mainly just to take traffic originating from inside the home or office LAN and to forward it along to the ISP, or Internet Service Provider. Once traffic is at the ISP, a way more sophisticated type of router takes over. These core routers form the backbone of the internet and are directly responsible for how we send and receive data all over the internet every single day. Core ISP routers don't just handle a lot more traffic than a home or small office router, they also have to deal with much more complexity in making decisions about where to send traffic. A core router usually has many different connections to many other routers. Routers share data with each other via a protocol known as BGP, or Border Gateway Protocol, that lets them learn about the most optimal paths to forward traffic. When you open a web browser and load a web page, the traffic between computers and the web servers could have traveled over dozens of different routers. The internet is incredibly large and complicated, and routers are global guides for getting traffic to the right places. All of the network devices you've just learned about exist so that computers can communicate with each other, whether they're in the same room or thousands of miles apart. We've been calling these devices nodes, and we'll keep doing that, but it's also important to understand the concepts of servers and clients. The simplest way to think of a server is as something that provides data to something requesting that data. The thing receiving the data is referred to as a client. While we often talk about nodes being servers or clients, the reason our definition uses a word as vague as something is because it's not just nodes that can be servers or clients. Individual computer programs running on the same node can be servers and clients to each other too. It's also important to call out that most devices aren't purely a server or a client. Almost all nodes are both at some point in time. Quite the multitasking overachievers. That all being said, in most network topographies, each node is primarily either a server or a client. Sometimes we refer to an email server as an email server, even though it's itself a client of a DNS server. Why? Because its primary reason for existing is to serve data to clients. Likewise, if a desktop machine occasionally acts as a server in the sense that it provides data to another computer, its primary reason for existing is to fetch data from servers so that the user at the computer can do their work. To sum up, a server is anything that can provide data to a client, but we also use the words to refer to the primary purpose of various nodes on our network. Got it? Cool. Now, it's time for a short, ungraded quiz to test you on the basics of these networking devices.
My name is Sergio Latour, and I'm a network engineer at Google. I officially work on the YouTube TV product. My team is called the Linear TV Operations Team, and basically we make sure that the live TV is always available for the customers. To put it simply, a network engineer is someone that will design the roads for the internet. It's never a typical day as a network engineer. It could be anywhere from break and fix issues, it could be meetings, it could be working on challenging problems or projects. I think specifically for me and most network engineers, it's going to be incident management. When you work on an operational team, you're the firefighters for the network. And if the network goes down, that means business will stop. So for my specific product, if our network goes down, that means viewers won't be able to enjoy TV. A recent incident for our team specifically was Hurricane Irma. We had a lot of TV services in Florida, and people are trying to use their cell phones to watch the news or anything like that. They won't be able to view the news. So we had to react and come up with a plan when that hurricane came, so the service was still available for people. I believe networking is really important to us because it is the roads to the internet. This is how we use our devices every day. Without networks, you wouldn't be able to enjoy the applications on your cell phone, the websites you go to. So it's hugely important. Without the network engineers and the network engineers building these roadways or these virtual roadways, you would not be able to enjoy these fun apps like Snapchat or Google Search.
In some ways, the physical layer of our network stack model is the most complex of all. Its main focus is on moving ones and zeros from one end of a link to the next. But very complicated mathematics, physics, and electrical engineering principles are at play to transmit huge volumes of data across tiny wires at incredible speeds. Luckily for us, most of that falls within a different realm. With you, an aspiring IT support specialist needs to know about the physical layer is much more approachable. By the end of this lesson, you should have a solid foundation in aspects of the physical layer that will allow you to properly troubleshoot networking issues and set up new networks. Let's dive in. The physical layer consists of devices and means of transmitting bits across computer networks. A bit is the smallest representation of data that a computer can understand. It's a 1 or a 0. These ones and zeros sent across networks at the lowest level are what make up the frames and packets of data that we'll learn about when we cover the other layers. The takeaway is that it doesn't matter whether you're streaming your favorite song, emailing your boss, or using an ATM. What you're really doing is sending ones and zeros across the physical layer of the many different networks between you and the server you're interacting with. A standard copper network cable, once connected to devices on both ends, will carry a constant electrical charge. Ones and zeros are sent across those network cables through a process called modulation. Modulation is a way of varying the voltage of this charge moving across the cable. When used for computer networks, this kind of modulation is more specifically known as line coding. It allows devices on either end of a link to understand that an electrical charge in a certain state is a 0, in another state is a 1. Through this seemingly simple technique, modern networks are capable of moving 10 billion ones and zeros across a single network cable every second. The most common type of cabling used for connecting computing devices is known as twisted pair. It's called a twisted pair cable because it features pairs of copper wires that are twisted together. These pairs act as a single conduit for information, and their twisted nature helps protect against electromagnetic interference and crosstalk from neighboring pairs. A standard Cat6 cable has 8 wires consisting of 4 twisted pairs inside a single jacket. Exactly how many pairs are actually in use depends on the transmission technology being used. But in all modern forms of networking, it's important to know that these cables allow for duplex communication. Duplex communication is the concept that information can flow in both directions across the cable. On the flip side, a process called simplex communication is unidirectional. Think about a baby monitor, where the transmission of data only goes in one direction, making it a simplex communication. A phone call, on the other hand, is duplex since both parties can listen and speak. The way networking cables ensure that duplex communication is possible is by reserving 1 or 2 pairs for communicating in one direction. They then use the other 1 or 2 pairs for communicating in the other direction. So, devices on either side of a networking link can both communicate with each other at the exact same time. This is known as full duplex. If there's something wrong with the connection, you might see a network link degrade and report itself as operating as half duplex. Half duplex means that while communication is possible in each direction, only one device can be communicating at a time. The final steps of how the physical layer works take place at the endpoints of our network links. Twisted pair network cables are terminated with a plug that takes the individual internal wires and exposes them. The most common plug is known as an RJ45 or registered jack 45. It's one of many cable plug specifications, but by far the most common in computer networking. A network cable with an RJ45 plug can connect to an RJ45 network port. Network ports are generally directly attached to the devices that make up a computer network. Switches would have many network ports because their purpose is to connect many devices, but servers and desktops usually only have 1 or 2. Your laptop, tablet, or phone probably don't have any, but we'll get to wireless networking in a later module. Most network ports have 2 small LEDs. One is the link light, and the other is the activity light. The link light will be lit when a cable is properly connected to 2 devices that are both powered on. The activity light will flash when data is actively transmitted across the cable. A long time ago, the flashing of an activity light corresponded directly to the ones and zeros being sent. Today, computer networks are so fast that the activity light doesn't really communicate much other than if there's any traffic or not. On switches, sometimes the same LED is used for both link and activity status. It might even indicate other things like link speed. You'll have to read up on a particular piece of hardware you're working with, but there will almost always be some troubleshooting data available to you through port lights. Sometimes a network port isn't connected directly to a device. Instead, there might be network ports mounted in a wall or underneath your desk. These ports are generally connected to the network via cables ran through the walls that eventually end at a patch panel. A patch panel is a device containing many network ports, but it does no other work. It's just a container for the endpoints of many runs of cable. Additional cables are then generally ran from a patch panel to switches or routers to provide network access to the computers at the other end of those links. Wireless and cellular internet access are quickly becoming some of the most common ways to connect computing devices to networks. And it's probably how you're connected right now. So you might be surprised to hear that traditional cable networks are still the most common option you find in the workplace and definitely in the data center. The protocol most widely used to send data across individual links is known as Ethernet. Ethernet and the data link layer provide a means for software at higher levels of the stack to send and receive data. One of the primary purposes of this layer is to essentially abstract away the need for any other layers to care about the physical layer and what hardware is in use. By dumping this responsibility on the data link layer, the internet, transport, and application layers can all operate the same no matter how the device they're running on is connected. So, for example, your web browser doesn't need to know if it's running on a device connected via a twisted pair or a wireless connection. It just needs the underlying layers to send and receive data for it. By the end of this lesson, you'll be able to explain what MAC addresses are and how they're used to identify computers. You'll also know how to describe the various components that make up an Ethernet frame, and you'll be able to differentiate between unicast, multicast, and broadcast addresses. Lastly, you'll be able to explain how cyclical redundancy checks help ensure the integrity of data sent via Ethernet. Understanding these concepts will help you troubleshoot a variety of problems as an IT support specialist. Warning, a history lesson on old school technology is headed your way. Here goes. Ethernet is a fairly old technology. It first came into being in 1980 and saw its first fully published standardization in 1983. Since then, a few changes have been introduced, primarily in order to support ever-increasing bandwidth needs. For the most part, though, the Ethernet in use today is comparable to the Ethernet standard as first published all those years ago. In 1983, computer networking was totally different than it is today. One of the notable differences in LAN topology was that the switch, or switchable hub, hadn't been invented yet. This meant that frequently, many or all devices on a network shared a single collision domain. You might remember from our discussion about hubs and switches that a collision domain is a network segment where only one device can speak at a time. This is because all data in a collision domain is sent to all the nodes connected to it. If two computers were to send data across the wire at the same time, this would result in literal collisions of the electrical current representing our ones and zeros, leaving the end result unintelligible. Ethernet as a protocol solved this problem by using a technique known as carrier sense multiple access with collision detection. Doesn't exactly roll off the tongue. We generally abbreviate this to CSMA-CD. CSMA-CD is used to determine when the communications channels are clear and when a device is free to transmit data. The way CSMA-CD works is actually pretty simple. If there's no data currently being transmitted on the network segment, a node will feel free to send data. If it turns out that two or more computers end up trying to send data at the same time, the computers detect this collision and stop sending data. Each device involved with the collision then waits a random interval of time before trying to send data again. This random interval helps to prevent all the computers involved in the collision from colliding again the next time they try to transmit anything. When a network segment is a collision domain, it means that all devices on that segment receive all communication across the entire segment. This means we need a way to identify which node the transmission was actually meant for. This is where something known as a Media Access Control Address, or MAC address, comes into play. A MAC address is a globally unique identifier attached to an individual network interface. It's a 48-bit number normally represented by 6 groupings of 2 hexadecimal numbers. Just like how binary is a way to represent numbers with only 2 digits, hexadecimal is a way to represent numbers using 16 digits. Since we don't have numerals to represent any individual digit larger than 9, hexadecimal numbers employ the letters A, B, C, D, E, and F to represent the numbers 10, 11, 12, 13, 14, and 15. Another way to reference each group of numbers in a MAC address is an octet. An octet in computer networking is any number that can be represented by 8 bits. In this case, 2 hexadecimal digits can represent the same numbers that 8 bits can. Now, you may have noticed that we mentioned that MAC addresses are globally unique, which might have left you wondering how that could possibly be. The short answer is that a 48-bit number is much larger than you might expect. The total number of possible MAC addresses that could exist is 2 to the power of 48, or 281,474,976,710,656 unique possibilities. That's a whole lot of possibilities. A MAC address is split into 2 sections. The first 3 octets of a MAC address are known as the Organizationally Unique Identifier, or OUI. These are assigned to individual hardware manufacturers by the IEEE, or the Institute of Electrical and Electronics Engineers. This is a useful bit of information to keep in your back pocket because it means that you can always identify the manufacturer of a network interface purely by its MAC address. The last 3 octets of a MAC address can be assigned in any way that the manufacturer would like, with the condition that they only assign each possible address once to keep all MAC addresses globally unique. Ethernet uses MAC addresses to ensure that the data it sends has both an address for the machine that sent the transmission as well as the one that the transmission was intended for. In this way, even on a network segment acting as a single collision domain, each node on that network knows when traffic is intended for it. So far, we've discussed ways for one device to transmit data to one other device. This is what's known as unicast. A unicast transmission is always meant for just one receiving address. At the Ethernet level, this is done by looking at a special bit in the destination MAC address. If the least significant bit in the first octet of a destination address is set to 0, it means that Ethernet frame is intended for only the destination address. This means it would be sent to all devices on the collision domain, but only actually received and processed by the intended destination. If the least significant bit in the first octet of a destination address is set to 1, it means you're dealing with a multicast frame. A multicast frame is similarly set to all devices on the local network segment. What's different is that it will be accepted or discarded by each device depending on criteria aside from their own hardware MAC address. Network interfaces can be configured to accept lists of configured multicast addresses for these sorts of communications. The third type of Ethernet transmission is known as broadcast. An Ethernet broadcast is sent to every single device on a LAN. This is accomplished by using a special destination known as a broadcast address. The Ethernet broadcast address is all Fs. Ethernet broadcasts are used so that devices can learn more about each other. Don't worry, you'll be learning more about broadcast and a technology known as address resolution protocol later in this course. But for now, let's move on to dissecting the Ethernet frame. To wrap up, we'll round out your understanding of the basics of networking by dissecting an Ethernet frame. Understanding the networking basics is the first step in building a really strong foundation of networking knowledge that you'll need in IT support. A data packet is an all-encompassing term that represents any single set of binary data being sent across a network link. The term data packet isn't tied to any specific layer or technology. It just represents a concept, one set of data being sent from point A to point B. Data packets at the Ethernet level are known as Ethernet frames. An Ethernet frame is a highly structured collection of information presented in a specific order. This way, network interfaces at the physical layer can convert a stream of bits traveling across a link into meaningful data, or vice versa. Almost all sections of an Ethernet frame are mandatory, and most of them have a fixed size. The first part of an Ethernet frame is known as the preamble. A preamble is 8 bytes, or 64 bits long, and can itself be split into 2 sections. The first 7 bytes are a series of alternating ones and zeros. These act partially as a buffer between frames and can also be used by the network interfaces to synchronize internal clocks they use to regulate the speed at which they send data. This last byte in the preamble is known as the SFD, or Start Frame Delimiter. This signals to a receiving device that the preamble is over and that the actual frame contents will now follow. Immediately following the Start Frame Delimiter comes the destination MAC address. This is the hardware address of the intended recipient, which is then followed by the source MAC address, or where the frame originated from. Don't forget that each MAC address is 48 bits, or 6 bytes long. The next part of an Ethernet frame is called the ether type field. It's 16 bits long and used to describe the protocol of the contents of the frame. We'll be doing a deep dive on what these protocols are a little later. It's worth calling out that instead of the ether type field, you could also find what's known as a VLAN header. It indicates that the frame itself is what's called a VLAN frame. If a VLAN header is present, the ether type field follows it. VLAN stands for virtual LAN. It's a technique that lets you have multiple logical LANs operating on the same physical equipment. Any frame with a VLAN tag will only be delivered out of a switch interface configured to relay that specific tag. This way, you can have a single physical network that operates like it's multiple LANs. VLANs are usually used to segregate different forms of traffic. So, you might see a company's IP phones operating on one VLAN, while all desktops operate on another. After this, you'll find the data payload of an Ethernet frame. A payload, in networking terms, is the actual data being transported, which is everything that isn't a header. The data payload of a traditional Ethernet frame can be anywhere from 46 to 1500 bytes long. This contains all of the data from higher layers, such as the IP, transport, and application layers that's actually being transmitted. Following that data, we have what's known as a frame check sequence. This is a 4-byte or 32-bit number that represents a checksum value for the entire frame. This checksum value is calculated by performing what's known as a cyclical redundancy check against the frame. A cyclical redundancy check, or CRC, is an important concept for data integrity and is used all over computing, not just network transmissions. A CRC is basically a mathematical transformation that uses polynomial division to create a number that represents a larger set of data. Anytime you perform a CRC against a set of data, you should end up with the same checksum number. The reason it's included in an Ethernet frame is so that the receiving network interface can infer if it received uncorrupted data. When a device gets ready to send an Ethernet frame, it collects all the information we just covered, like the destination and originating MAC addresses, the data payload, and so on. Then it performs a CRC against that data and attaches the resulting checksum number as the frame check sequence at the end of the frame. This data is then sent across a link and received at the other end. Here, all the various fields of the Ethernet frame are collected, and now the receiving side performs a CRC against that data. If the checksum computed by the receiving end doesn't match the checksum in the frame check sequence field, the data is thrown out. This is because some amount of data must have been lost or corrupted during transmission. It's then up to a protocol at a higher layer to decide if that data should be retransmitted. Ethernet itself only reports on data integrity. It doesn't perform data recovery. You've gotten the basics of networking down. Nice work. Next up is a quiz. You got this. But even if you don't, just review the material until you get more comfortable with this stuff. If you are interested in IT and you never went to school for it, you don't have a CS degree, anything like that, I always tell people that half the people that I've worked with at Google do not have a traditional IT background. I've worked with people in IT who were teachers. I knew people that were drama majors, that were history majors, chemists. It has nothing to do with it, right? It's all about being able to connect with people, being able to look at a problem and break it down into components that are each pretty easy to solve on their own until you get the whole thing solved. That's it, right? Learning the technical piece is easy. Anyone can learn that piece. For one, I tell them, just go get your hands dirty, right? There's a lot of places where you can kind of just go and do this, even at home, right? You probably have a wireless network or something, go break it, right? Go do that, get your hands dirty, try it out. Set up a virtual machine and go and break it 100 different ways, and then figure out all the different ways you can fix it. It's gonna give you the most practical experience into it. And you're gonna figure out whether finding the problems is actually something that gets you excited, oh, cool, I figured this out. Yeah, and it'll tell you whether this is the right field for you. I wouldn't be dissuaded just because you don't think you have a technical background. The technical background piece is the least important piece. Computers are able to communicate across massive distances at near instant speeds. It's a remarkable technical advancement at the root of how billions of people use the internet every single day. Earlier in this course, we learned about how computers communicate with each other over short distances or on a single network segment, or LAN. In these next lessons, we'll focus on the technologies that allow data to cross many networks, facilitating communications over great distances. By the end of this module, you'll be able to describe the IP addressing scheme and how subnetting works. This means you'll learn how to perform basic math in binary in order to describe subnets. You'll also be able to demonstrate how encapsulation works and how protocols such as ARP allow different layers of the network to communicate. And finally, you'll gain an understanding of the basics behind routing protocols, and how the internet works. For now, route yourself to the next video and we'll get started. On a local area network, or LAN, nodes can communicate with each other through their physical MAC addresses. This works well on small scale because switches can quickly learn the MAC addresses connected to each of their ports to forward transmissions appropriately. But MAC addressing isn't a scheme that scales well. Every single network interface on the planet has a unique MAC address, and they aren't ordered in any sort of systematic way. There's no way of knowing where on the planet a certain MAC address might be at any one point in time, so it's not ideal for communicating across distances. Later on in this lesson, when we introduce ARP, or Address Resolution Protocol, you'll see that the way that nodes learn about each other's physical addressing isn't translatable to anything besides a single network segment anyway. Clearly, we need another solution. And that is the network layer, and the Internet Protocol, or IP, and the IP addresses that come along with it. By the end of this lesson, you'll be able to identify an IP address, describe how IP datagrams are encapsulated inside the payload of an Ethernet frame, and correctly identify and describe the many fields of an IP datagram header. IP addresses are 32-bit long numbers made up of 4 octets, and each octet is normally described in decimal numbers. 8 bits of data, or a single octet, can represent all decimal numbers from 0 to 255. For example, 12.34.56.78 is a valid IP address, but 123.456.789.100 would not be, because it has numbers larger than could be represented by 8 bits. This format is known as dotted decimal notation. We'll deep dive into how some of this works in an upcoming lesson about subnetting. The important thing to know for now is that IP addresses are distributed in large sections to various organizations and companies, instead of being determined by hardware vendors. This means that IP addresses are more hierarchical and easier to store data about than physical addresses are. Think of IBM, which owns every single IP that has the number 9 as the first octet. At a very high level, this means that if an internet router needs to figure out where to send a data packet intended for the IP address 9.0.0.1, that router only has to know to get it to one of IBM's routers. That router can handle the rest of the delivery process from there. It's important to call out that IP addresses belong to the networks, not the devices attached to those networks. So your laptop will always have the same MAC address no matter where you use it, but it'll have a different IP address assigned to it at an internet cafe than it would when you're at home. The LAN at the internet cafe or the LAN at your house would each be individually responsible for handing out an IP address to your laptop if you power it on there. On a day-to-day basis, getting an IP address is usually a pretty invisible process. You'll learn more about some of the technologies at play in a later lesson. For now, remember that on many modern networks, you can connect a new device and an IP address will be assigned to it automatically through a technology known as Dynamic Host Configuration Protocol. An IP address assigned this way is known as a dynamic IP address. The opposite of this is known as a static IP address, which must be configured on a node manually. In most cases, static IP addresses are reserved for servers and network devices, while dynamic IP addresses are reserved for clients. But there are certainly situations where this might not be true. Just like how the data packets at the Ethernet layer have a specific name, Ethernet frames, so do packets at the network layer. Under the IP protocol, a packet is usually referred to as an IP datagram. Just like any Ethernet frame, an IP datagram is a highly structured series of fields that are strictly defined. The two primary sections of an IP datagram are the header and the payload. You'll notice that an IP datagram header contains a lot more data than an Ethernet frame header does. The very first field is 4 bits and indicates what version of Internet Protocol is being used. The most common version of IP is version 4, or IPv4. Version 6, or IPv6, is rapidly seeing more widespread adoption, but we'll cover that in a later module. After the version field, we have the header length field. This is also a 4-bit field that declares how long the entire header is. This is almost always 20 bytes in length when dealing with IPv4. In fact, 20 bytes is the minimum length of an IP header. You couldn't fit all the data you need for a properly formatted IP header in any less space. Next, we have the service type field. These 8 bits can be used to specify details about quality of service, or QoS technologies. The important takeaway about QoS is that there are services that allow routers to make decisions about which IP datagram may be more important than others. The next field is a 16-bit field known as the total length field. It's used for exactly what it sounds like, to indicate the total length of the IP datagram it's attached to. The identification field is a 16-bit number that's used to group messages together. IP datagrams have a maximum size, and you might already be able to figure out what that is. Since the total length field is 16 bits, and this field indicates the size of an individual datagram, the maximum size of a single datagram is the largest number you can represent with 16 bits, 65,535. If the total amount of data that needs to be sent is larger than what can fit in a single datagram, the IP layer needs to split this data up into many individual packets. When this happens, the identification field is used so that the receiving end understands that every packet with the same value in that field is part of the same transmission. Next up, we have 2 closely related fields, the flag field and the fragmentation offset field. The flag field is used to indicate if a datagram is allowed to be fragmented or to indicate that the datagram has already been fragmented. Fragmentation is the process of taking a single IP datagram and splitting it up into several smaller datagrams. While most networks operate with similar settings in terms of what size an IP datagram is allowed to be, sometimes this could be configured differently. If a datagram has to cross from a network allowing a larger datagram size to one with a smaller datagram size, the datagram would have to be fragmented into smaller ones. The fragmentation offset field contains values used by the receiving end to take all the parts of a fragmented packet and put them back together in the correct order. Let's move along to the time to live, or TTL field. This field is an 8-bit field that indicates how many router hops a datagram can traverse before it's thrown away. Every time a datagram reaches a new router, that router decrements the TTL field by 1. Once this value reaches 0, a router knows it doesn't have to forward the datagram any further. The main purpose of this field is to make sure that when there's a misconfiguration in routing that causes an endless loop, datagrams don't spend all eternity trying to reach their destination. An endless loop could be when router A thinks router B is the next hop, and router B thinks router A is the next hop. Spoiler alert, in an upcoming module, you'll learn that the TTL field has valuable troubleshooting qualities, but secrets like these are only released to those who keep going. After the TTL field, you'll find the protocol field. This is another 8-bit field that contains data about what transport layer protocol is being used. The most common transport layer protocols are TCP and UDP, and we'll cover both of those in detail in the next few lessons. So next, we find the header checksum field. This field is a checksum of the contents of the entire IP datagram header. It functions very much like the Ethernet checksum field we discussed in the last module. Since the TTL field has to be recomputed at every router that a datagram touches, the checksum field necessarily changes too. After all of that, we finally get to two very important fields, the source and destination IP address fields. Remember that an IP address is a 32-bit number, so it should come as no surprise that these fields are each 32 bits long. Up next, we have the IP options field. This is an optional field and is used to set special characteristics for datagrams primarily used for testing purposes. The IP options field is usually followed by a padding field. Since the IP options field is both optional and variable in length, the padding field is just a series of zeros used to ensure the header is the correct total size. Now that you know about all of the parts of an IP datagram, you might wonder how this relates to what we've learned so far. You might remember that in our breakdown of an Ethernet frame, we mentioned a section we described as the data payload section. This is exactly what the IP datagram is, and this process is known as encapsulation. The entire contents of an IP datagram are encapsulated as the payload of an Ethernet frame. You might have picked up on the fact that our IP datagram also has a payload section. The contents of this payload are the entirety of a TCP or UDP packet, which we'll cover later. Hopefully, this helps you better understand why we talk about networking in terms of layers. Each layer is needed for the one above it. IP addresses can be split into two sections, the network ID and the host ID. Earlier, we mentioned that IBM owns all IP addresses that have a 9 as the value of the first octet in an IP address. If we take an example IP address of 9.100.100.100, the network ID would be the first octet, and the host ID would be the second, third, and fourth octets. The address class system is a way of defining how the global IP address space is split up. There are three primary types of address classes: Class A, Class B, and Class C. Class A addresses are those where the first octet is used for the network ID, and the last three are used for the host ID. Class B addresses are where the first two octets are used for the network ID, and the second two are used for the host ID. Class C addresses, as you might have guessed, are those where the first 3 octets are used for the network ID, and only the final octet is used for the host ID. Each address class represents a network of vastly different size. For example, since a Class A network has a total of 24 bits of host ID space, this comes out to 2 to the 24th, or 16,777,216 individual addresses. Compare this with a Class C network, which only has 8 bits of host ID space. For a Class C network, this comes out to 2 to the 8th, or 256 addresses. You can also tell exactly what address class an IP address belongs to just by looking at it. If the very first bit of an IP address is a 0, it belongs to a Class A network. If the first bits are 1, 0, it belongs to a Class B network. Finally, if the first bits are 1, 1, 0, it belongs to a Class C network. Since humans aren't great at thinking in binary, it's good to know that this also translates nicely to how these addresses are represented in dotted decimal notation. You might remember that each octet in an IP address is 8 bits, which means each octet can take a value between 0 and 255. If the first bit has to be a 0, as it is with the Class A address, the possible values for the first octet are 0 through 127. This means that any IP address with a first octet with one of those values is a Class A address. Similarly, Class B addresses are restricted to those that begin with the first octet value of 128 through 191. And Class C addresses begin with the first octet value of 192 through 223. You might notice that this doesn't cover every possible IP address. That's because there are 2 other IP address classes, but they're not quite as important to understand. Class D addresses always begin with the bits 1110 and are used for multicasting, which is how a single IP datagram can be sent to an entire network at once. These addresses begin with decimal values between 224 and 239. Lastly, Class C addresses make up all of the remaining IP addresses, but they're unassigned and only used for testing purposes. In practical terms, this class system has mostly been replaced by a system known as CIDR, or classless interdomain routing. But the address class system is still in place in many ways and is important to understand for anyone looking for a well-rounded networking education. And you know we're all about that. So don't worry, we'll be covering CIDR in a future lesson. Congrats! You now understand how both MAC addresses are used at the data link layer and how IP addresses are used at the network layer. Now we need to discuss how these 2 separate address types relate to each other. This is where Address Resolution Protocol, or ARP, comes into play. ARP is a protocol used to discover the hardware address of a node with a certain IP address. Once an IP datagram has been fully formed, it needs to be encapsulated inside an Ethernet frame. This means that the transmitting device needs a destination MAC address to complete the Ethernet frame header. Almost all network-connected devices will retain a local ARP table. An ARP table is just a list of IP addresses and the MAC addresses associated with them. Let's say we want to send some data to the IP address 10.20.30.40. It might be the case that this destination doesn't have an entry in the ARP table. When this happens, the node that wants to send data sends a broadcast ARP message to the MAC broadcast address, which is all Fs. These kinds of broadcast ARP messages are delivered to all computers on the local network. When the network interface that's been assigned an IP of 10.20.30.40 receives this ARP broadcast, it sends back what's known as an ARP response. This response message will contain the MAC address for the network interface in question. Now, the transmitting computer knows what MAC address to put in the destination hardware address field, and the Ethernet frame is ready for delivery. It'll also likely store this IP address in its local ARP table so that it won't have to send an ARP broadcast the next time it needs to communicate with this IP. Handy. ARP table entries generally expire after a short amount of time to ensure changes in the network are accounted for. So don't expect it to stick around the way I expect you to stick around for the next ungraded quiz.
My name is Sergio Latour, and I'm a network engineer at Google. When I was just a young kid, I liked analog tools like screwdrivers and drills, and then I liked taking things apart. And then as I got older in my teenage years, I realized I could take apart computers, and then that really interested me because when you opened it up, it was like fans, like lights, like the circuitry, and I just didn't understand it. It didn't make sense to me, but if I knew if I put it together the right way, I could actually interact with it and have fun and play my video games off of it, and that's kind of how it really started. And then by the time when I got a little older, outside of high school, I realized I could make this like a passion and actually like really learn how this technology works. I think the favorite part is solving the problems. I really enjoy when we get to see data go from one device to another and how things communicate and how the customers get to enjoy it. I've gained so many different tools and skills, and now I feel like a Swiss Army knife when I'm working, and there's so many different experiences I can bring back to solve problems I face today. Early, starting off as an entry-level network technician, I had a project to upgrade a firewall for a police department. And the firewall basically is the security appliance and the entry point to the network. We thought it worked, it went through successfully until I got a phone call very late at night that things were broken. And when we realized that emails and police calls were not going through and that the upgrade failed. And at that point I realized the magnitude of the things that I am working on can affect people's lives, and it can cause harm and it can cause good. So it was really a good humbling experience for me when I was working on that project.
In the most basic of terms, subnetting is the process of taking a large network and splitting it up into many individual smaller subnetworks, or subnets. By the end of this lesson, you'll be able to explain why subnetting is necessary and describe how subnet masks extend what's possible with just network and host IDs. You'll also be able to discuss how a technique known as CIDR allows for even more flexibility than plain subnetting. Lastly, you'll be able to apply some basic binary math techniques to better understand how all of this works. Incorrect subnetting setups are a common problem you might run into as an IT support specialist, so it's important to have a strong understanding of how this works. That's a lot, so let's dive in. As you might remember from the last lesson, address classes give us a way to break the total global IP space into discrete networks. If you want to communicate with the IP address 9.100.100.100, core routers on the internet know that this IP belongs to the 9.0.0.0 Class A network. They then route the message to the gateway router responsible for the network by looking at the network ID. A gateway router specifically serves as the entry and exit path to a certain network. You can contrast this with core internet routers, which might only speak to other core routers. Once your packet gets to the gateway router for the 9.0.0.0 Class A network, that router is now responsible for getting that data to the proper system by looking at the host ID. This all makes sense until you remember that a single Class A network contains 16,777,216 individual IPs. That's just way too many devices to connect to the same router. This is where subnetting comes in. With subnets, you can split your large network up into many smaller ones. These individual subnets will all have their own gateway routers, serving as the ingress and egress point for each subnet. So far, we've learned about network IDs, which are used to identify networks, and host IDs, which are used to identify individual hosts. If we want to split things up even further, and we do, we'll need to introduce a third concept, the subnet ID. You might remember that an IP address is just a 32-bit number. In a world without subnets, a certain number of these bits are used for the network ID, and a certain number of the bits are used for the host ID. In a world with subnetting, some bits that would normally comprise the host ID are actually used for the subnet ID. With all three of these IDs representable by a single IP address, we now have a single 32-bit number that can be accurately delivered across many different networks. At the internet level, core routers only care about the network ID and use this to send the datagram along to the appropriate gateway router to that network. That gateway router then has some additional information that it can use to send the datagram along to the destination machine, or the next router in the path to get there. Finally, the host ID is used by that last router to deliver the datagram to the intended recipient machine. Subnet IDs are calculated via what's known as a subnet mask. Just like an IP address, subnet masks are 32-bit numbers that are normally written out as 4 octets in decimal. The easiest way to understand how subnet masks work is to compare one to an IP address. Warning, dense material ahead. We're about to get into some tough material, but it's super important to properly understand how subnet masks work because they're so frequently misunderstood. Subnet masks are often glossed over as magic numbers. People just memorize some of the common ones without fully understanding what's going on behind the scenes. In this course, we're really trying to ensure that you leave with a well-rounded networking education. So even though subnet masks can seem tricky at first, stick with it and you'll get the hang of it in no time. Just know that in the next video, we'll be covering some additional basics of binary math. Feel free to watch this video a second or third time after reviewing the material. Go at your own pace and you'll get there in the perfect amount of time. Let's work with the IP address 9.100.100.100 again. You might remember that each part of an IP address is an octet, which means that it consists of 8 bits. The number 9 in binary is just 1001. But since each octet needs 8 bits, we need to pad it with some zeros in front. As far as an IP address is concerned, having a number 9 as the first octet is actually represented as 00001001. Similarly, the numeral 100 as an 8-bit number is 01100100. So the entire binary representation of the IP address 9.100.100.100 is a lot of ones and zeros. A subnet mask is a binary number that has 2 sections. The beginning part, which is the mask itself, is a string of ones. Just zeros come after this. The subnet mask, which is the part of the number with all the ones, tells us what we can ignore when computing a host ID. The part with all the zeros tells us what to keep. Let's use the common subnet mask of 255.255.255.0. This would translate to 24 ones followed by 8 zeros. The purpose of the mask, or the part that's all ones, is to tell a router what part of an IP address is the subnet ID. You might remember that we already know how to get the network ID for an IP address. For 9.100.100.100, a Class A network, we know that this is just the first octet. This leaves us with the last 3 octets. Let's take those remaining octets and imagine them next to the subnet mask in binary form. The numbers in the remaining octets that have a corresponding 1 in the subnet mask are the subnet ID. The numbers in the remaining octets that have a corresponding 0 are the host ID. The size of a subnet is entirely defined by its subnet mask. So for example, with a subnet mask of 255.255.255.0, we know that only the last octet is available for host IDs, regardless of what size the network and subnet IDs are. A single 8-bit number can represent 256 different numbers, or more specifically, the numbers 0 through 255. This is a good time to point out that, in general, a subnet can usually only contain 2 less than the total number of host IDs available. Again, using a subnet mask of 255.255.255.0, we know that the octet available for host IDs can contain the numbers 0 through 255, but 0 is generally not used, and 255 is normally reserved as a broadcast address for the subnet. This means that really only the numbers 1 through 254 are available for assignment to a host. While this total number less than 2 approach is almost always true, generally speaking, you'll refer to the number of hosts available in a subnet as the entire number. So even if it's understood that 2 addresses aren't available for assignment, you'd still say that 8 bits of host ID space have 256 addresses available, not 254. This is because those other IPs are still IP addresses, even if they aren't assigned directly to a node on that subnet. Now, Let's look at a subnet mask that doesn't draw its boundaries at an entire octet, or 8 bits of address. The subnet mask 255.255.255.224 would translate to 27 ones followed by 5 zeros. This means that we have 5 bits of host ID space, or a total of 32 addresses. This brings up a shorthand way of writing subnet masks. Let's say we're dealing with our old friend 9.100.100.100 with a subnet mask of 255.255.255.224. Since that subnet mask represents 27 ones followed by 5 zeros, a quicker way of referencing this is with the notation /27. The entire IP and subnet mask could be written out as 9.100.100.100/27. Neither notation is necessarily more common than the other, so it's important to understand both. That was a lot. Make sure to go back and watch this video again if you need a refresher. Or if you're a total whiz, you can move on to the next video on basic binary math. I'll see you there, or maybe here. Binary numbers can seem intimidating at first, since they look so different from decimal numbers. But as far as the basics go, the math behind counting, adding, or subtracting binary numbers is exactly the same as with decimal numbers. It's important to call out that there aren't different kinds of numbers. Numbers are universal. There are only different notations for how to reference them. Humans, most likely because most of us have 10 fingers and 10 toes, decided on using a system with 10 individual numerals used to represent all numbers. The numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 can be combined in ways to represent any whole number in existence. Because there are 10 total numerals in use in a decimal system, another way of referring to this is as base 10. Because of the constraints of how logic gates work inside of a processor, it's way easier for computers to think of things only in terms of 0 and 1. This is also known as binary, or base 2. You can represent all whole numbers in binary in the same way you can in decimal. It just looks a little different. When you count in decimal, you move through all the numerals upward until you run out. Then you add a second column with a higher significance. Let's start counting at 0 until we get to 9. Once we get to 9, we basically just start over. We add a 1 to a new column, then start over at 0 in the original column. We repeat this process over and over in order to count all whole numbers. Counting in binary is exactly the same. It's just that you only have 2 numerals available. You start with 0, which is the same as 0 in decimal, then you increment once. Now you have 1, which is the same as 1 in decimal. Since we've already run out of numerals to use, it's time to add a new column. So now we have the number 1, 0, which is the same as 2 in decimal. 1, 1 is 3. 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, 1, 1, 1 is 7, etc. It's the exact same thing we do with decimal, just with fewer numerals at our disposal. When working with various computing technologies, you'll often run into the concept of bits, or ones and zeros. There's a pretty simple trick to figure out how many decimal numbers can be represented by a certain number of bits. If you have an 8-bit number, you can just perform the math 2 to the power of 8. This gives you 256, which lets you know that an 8-bit number can represent 256 decimal numbers. Or put another way, the numbers 0 through 255. A 4-bit number would be 2 to the power of 4, or 16 total numbers. A 16-bit number would be 2 to the power of 16, or 65,536 numbers. In order to tie this back to what you might already know, this trick doesn't only work for binary. It works for any number system. It's just the base changes. You might remember that we can also refer to binary as base 2 and decimal as base 10. All you need to do is swap out the base for what's being raised to the number of columns. For example, let's take a base 10 number with 2 columns of digits. This would translate to 10 to the power of 2. 10 to the power of 2 equals 100, which is exactly how many numbers you can represent with 2 columns of decimal digits. or the numbers 0 through 99. Similarly, 10 to the power of 3 is 1000, which is exactly how many numbers you can represent with 3 columns of decimal digits, or the numbers 0 through 999. Not only is counting in different bases the same, so is simple arithmetic like addition. In fact, binary addition is even simpler than any other base, since you only have 4 possible scenarios. 0 plus 0 equals 0, just like in decimal. 0 plus 1 equals 1, and 1 plus 0 equals 1. Should also look familiar. 1 plus 1 equals 1, 0. Looks a little different, but should still make sense. You carry a digit to the next column once you reach 10 in doing decimal addition. You carry a digit to the next column once you reach 2 when doing binary addition. Addition is what's known as an operator, and there are many operators that computers use to make calculations. 2 of the most important operators are OR and AND. In computer logic, a 1 represents true, and a 0 represents false. The way the OR operator works is you look at each digit, and if either of them is true, the result is true. The basic equation is x or y equals z, which could be read as if either x or y is true, then z is true. Otherwise, it's false. Therefore, 1 or 0 equals 1, but 0 or 0 equals 0. The operator AND does what it sounds like it does. It returns true if both values are true. Therefore, 1 and 1 equals 1, but 1 and 0 equals 0, and 0 and 0 equals 0, and so on. Now, you might be wondering why we've covered all of this. No, it's not to confuse you. It's all really to help explain subnet masks a bit more. A subnet mask is a way for a computer to use AND operators to determine if an IP address exists on the same network. This means that the host ID portion is also known, since it'll be anything left out. Let's use the binary representation of our favorite IP address, 9.100.100.100, and our favorite subnet mask, 255.255.255.0. Once you put one on top of the other and perform a binary AND operator on each column, you'll notice that the result is the network ID and subnet ID portion of our IP address, or 9.100.100. The computer that just performed this operation can now compare the result with its own network ID to determine if the address is on the same network or a different one. I bet you never thought you'd have a favorite IP address or subnet, but that's what happens in the wonderful world of basic binary math. Address classes were the first attempt at splitting up the global internet IP space. Subnetting was introduced when it became clear that address classes themselves weren't a sufficient way of keeping everything organized. But as the internet continued to grow, traditional subnetting just couldn't keep up. With traditional subnetting and the address classes, the network ID is always either 8-bit for Class A networks, 16-bit for Class B networks, or 24 bits for Class C networks. This means that there might only be 254 Class A networks in existence, but it also means there are 2,097,152 potential Class C networks. That's a lot of entries in a routing table. To top it all off, the sizing of these networks aren't always appropriate for the needs of most businesses. 254 hosts in a Class C network is too small for many use cases, but the 65,534 hosts available for use in a Class B network is often way too large. Many companies ended up with various adjoining Class C networks to meet their needs. That meant that routing tables ended up with a bunch of entries for a bunch of Class C networks that were all actually being routed to the same place. This is where CIDR, or classless interdomain routing, comes into play. CIDR is an even more flexible approach to describing blocks of IP addresses. It expands on the concept of subnetting by using subnet masks to demarcate networks. To demarcate something means to set something off. When discussing computer networking, you'll often hear the term demarcation point to describe where one network or system ends and another one begins. In our previous model, we relied on a network ID, subnet ID, and host ID to deliver an IP datagram to the correct location. With CIDR, the network ID and subnet ID are combined into one. CIDR is where we get the shorthand slash notation that we discussed in the earlier video on subnetting. This slash notation is also known as CIDR notation. CIDR basically just abandons the concept of address classes entirely, allowing an address to be defined by only two individual IDs. Let's take 9.100.100.100 with a net mask of 255.255.255.0. Remember, this can also be written as 9.100.100.100/24. In a world where we no longer care about the address class of this IP, all we need is what the network mask tells us to determine the network ID. In this case, that would be 9.100.100. The host ID remains the same. This practice not only simplifies how routers and other network devices need to think about parts of an IP address, but it also allows for more arbitrary network sizes. Before, network sizes were static. Think only Class A, Class B, or Class C, and only subnets could be of different sizes. CIDR allows for networks themselves to be differing sizes. Before this, if a company needed more addresses than a single Class C could provide, they'd need an entire second Class C. With CIDR, they could combine that address space into one contiguous chunk with a net mask of /23, or 255.255.254.0. This means that routers now only need to know one entry in their routing table to deliver traffic to these addresses instead of two. It's also important to call out that you get additional available host IDs out of this practice. Remember that you always lose two host IDs per network. So if a /24 network has 2 to the 8 or 256 potential hosts, you really only have 256 minus 2, or 254 available IPs to assign. If you need two networks of this size, you have a total of 254 plus 254, or 508 hosts. A single /23 network, on the other hand, is 2 to the 9, or 512. 512 minus 2, 510 hosts. Take a second and lock that into your memory. Then when you're ready, we have a short ungraded quiz for you before we move on to routing in the next lesson. The internet is an incredibly impressive technological achievement. It meshes together millions of individual networks and allows communications to flow between them. From almost anywhere in the world, you can now access data from almost anywhere else, often in just fractions of a second. The way communications happen across all these networks, allowing you to access data from the other side of the planet, is through routing. By the end of this lesson, you'll be able to describe the basics of routing and how routing tables work. You'll be able to define some of the major routing protocols and what they do, and identify non-routable address space and how it's used. You'll also gain an understanding of the RFC system and how it made the internet what it is today. All of these are very important skills in order to troubleshoot the networking issues you might run into as an IT support specialist. Routing is one of those things that is both very simple and very complex. At a very high level, what routing is and how routers work is actually pretty simple. But underneath the hood, routing is a very complex and technologically advanced topic. Entire books have been written about the topic. Today, most intensive routing issues are almost exclusively handled by ISPs and only the largest of companies. We'll arm you with the basic overview of routing to give you a well-rounded networking education, since it's an important topic to understand no matter what. But by no means will our coverage be exhaustive. From a very basic standpoint, a router is a network device that forwards traffic depending on the destination address of that traffic. A router is a device that has at least two network interfaces, since it has to be connected to two networks to do its job. Basic routing has just a few steps. 1. A router receives a packet of data on one of its interfaces. 2. The router examines the destination IP of this packet. 3. The router then looks up the destination network of this IP in its routing table. 4, the router forwards that out through the interface that's closest to the remote network, as determined by additional info within the routing table. These steps are repeated as often as needed until the traffic reaches its destination. Let's imagine a router connected to 2 networks. We'll call the first network Network A, and give it an address space of 192.168.1.0/24. We'll call the second network Network B, and give it an address space of 10.0.0.0/24. The router has an interface on each network. On network A, it has an IP of 192.168.1.1, and on network B, it has an IP of 10.0.0.254. Remember, IP addresses belong to networks, not individual nodes on a network. A computer on network A with an IP address of 192.168.1.100 sends a packet to the address 10.0.0.10. This computer knows that 10.0.0.10 isn't on its local subnet, so it sends this packet to the MAC address of its gateway, the router. The router's interface on network A receives the packet because it sees that destination MAC address belongs to it. The router then strips away the data link layer encapsulation, leaving the network layer contents, the IP datagram. Now, the router can directly inspect the IP datagram header for the destination IP field. It finds the destination IP of 10.0.0.10. The router looks at its routing table and sees that network B, or the 10.0.0.0/24 network, is the correct network for the destination IP. It also sees that this network is only one hop away. In fact, since it's directly connected, the router even has the MAC address for this IP in its ARP table. Next, the router needs to form a new packet to forward along to network B. It takes all of the data from the first IP datagram and duplicates it. But it decrements the TTL field by 1 and calculates a new checksum. Then it encapsulates this new IP datagram inside of a new Ethernet frame. This time, it sets its own MAC address of the interface on network B as the source MAC address. Since it has the MAC address of 10.0.0.10 in its ARP table, it sets that as the destination MAC address. Lastly, the packet is sent out of its interface on network B, and the data finally gets delivered to the node living at 10.0.0.10. That's a pretty basic example of how routing works, but let's make it a little more complicated and introduce a third network. Everything else is still the same. We have network A, whose address space is 192.168.1.0/24. We have network B, whose address space is 10.0.0.0/24. The router that bridges these two networks still has the IPs of 192.168.1.1 on network A and 10.0.0.254 on network B. But let's introduce a third network, network C. It has an address space of 172.16.1.0/23. There's a second router connecting network B and network C. Its interface on network B has an IP of 10.0.0.1, and its interface on network C has an IP of 172.16.1.1. This time around, our computer at 192.168.1.100 wants to send some data to the computer that has an IP of 172.16.1.100. We'll skip the data link layer stuff, but remember that it's still happening, of course. The computer at 192.168.1.100 knows that 172.16.1.100 is not on its local network, so it sends the packet to its gateway, the router between network A and network B. Again, the router inspects the content of this packet. It sees a destination address of 172.16.1.100, and through a lookup of its routing table, it knows that the quickest way to get to the 172.16.1.0/23 network is via another router, with an IP of 10.0.0.1. The router decrements the TTL field and sends it along to the router of 10.0.0.1. This router then goes through the motions, knows that the destination IP of 172.16.1.100 is directly connected, and forwards the packet to its final destination. That's the basics of routing. The only difference between our examples and how things work on the internet is scale. Routers are usually connected to many more than just two networks. Very often, your traffic may have to cross a dozen routers before it reaches its final destination. And finally, in order to protect against breakages, core internet routers are typically connected in a mesh, meaning that there might be many different paths for a packet to take. Still, the concepts are all the same. Routers inspect the destination IP, look at their routing table to determine which path is the quickest, and forward the packet along the path. This happens over and over, every single packet making up every single bit of traffic all over the internet at all times. Pretty cool stuff, huh? During our earlier video on the basics of routing, you might have noticed a bunch of references to something known as a routing table. Routing itself is a pretty simple concept, and you'll find that routing tables aren't that much more complicated. The earliest routers were just regular computers of the era. They had two network interfaces, bridged two networks, and had a routing table that was manually updated. In fact, all major operating systems today still have a routing table that they consult before transmitting data. You could still build your own router today if you had a computer with two network interfaces and a manually updated routing table. Routing tables can vary a ton depending on the make and class of the router, but they all share a few things in common. The most basic routing table will have 4 columns. Destination network. This column would contain a row for each network that the router knows about. This is just the definition of the remote network, a network ID and a net mask. These could be stored in one column in CIDR notation, or the network ID and net mask might be in a separate column. Either way, it's the same concept. The router has a definition for a network and therefore knows what IP addresses might live on that network. When the router receives an incoming packet, it examines the destination IP address and determines which network it belongs to. A routing table will generally have a catch-all entry that matches any IP address that it doesn't have an explicit network listing for. Next hop. This is the IP address of the next router that should receive data intended for the destination network in question. Or this could just state the network is directly connected and that there aren't any additional hops needed. Total hops. This is the crucial part to understand routing and how routing tables work. On any complex network, like the internet, there will be lots of different paths to get from point A to point B. Routers try to pick the shortest possible path at all times to ensure timely delivery of data, but the shortest possible path to a destination network is something that could change over time, sometimes rapidly. Intermediary routers could go down, links could become disconnected, new routers could be introduced, traffic congestion could cause certain routes to become too slow to use. We'll get to know how routers know the shortest path in an upcoming video. For now, it's just important to know that for each next hop and each destination network, the router will have to keep track of how far away that destination currently is. That way, when it receives updated information from neighboring routers, it'll know if it currently knows about the best path or if a new, better path is available. Interface. The router also has to know which of its interfaces it should forward traffic matching the destination network out of. In most cases, routing tables are pretty simple. The really impressive part is that many core internet routers have millions of rows in their routing tables. These must be consulted for every single packet that flows through a router on its way to its final destination. What's also impressive is how much you've learned about routers, routing, and routing tables. Nice work. I'll see you in the next video on interior gateway protocols. We've covered the basics of how routing works and how routing tables are constructed, and they're both really pretty basic concepts. The real magic of routing is in the way that routing tables are always updated with new information about the quickest paths to destination networks. The protocols we'll be learning about in this video will help you identify routing problems on any network you might support. In order to learn about the world around them, routers use what are known as routing protocols. These are special protocols the routers use to speak to each other in order to share what information they might have. This is how a router on one side of the planet can eventually learn about the best path to a network on the other side of the planet. Routing protocols fall into two main categories: interior gateway protocols and exterior gateway protocols. Interior gateway protocols are further split into two categories: link state routing protocols and distance vector protocols. In this video, we'll cover the basics of interior gateway protocols. Interior gateway protocols are used by routers to share information within a single autonomous system. In networking terms, an autonomous system is a collection of networks that all fall under the control of a single network operator. The best example of this would be a large corporation that needs to route data between their many offices, and each of which might have their own local area network. Another example is the many routers employed by an internet service provider whose reaches are usually national in scale. You can contrast this with exterior gateway protocols, which are used for the exchange of information between independent autonomous systems. Spoiler alert, we'll cover exterior gateway protocols in an upcoming video. The two main types of interior gateway protocols are link state routing protocols and distance vector protocols. Their goals are super similar, but the routers that employ them share different kinds of data to get the job done. Distance vector protocols are an older standard. A router using a distance vector protocol basically just takes its routing table, which is a list of every network known to it and how far away these networks are in terms of hops. Then the router sends this list to every neighboring router, which is basically every router directly connected to it. In computer science, a list is known as a vector. This is why a protocol that just sends a list of distances to networks is known as a distance vector protocol. With a distance vector protocol, routers don't really know that much about the total state of an autonomous system. They just have some information about their immediate neighbors. For a basic glimpse into how distance vector protocols work, let's look at how two routers might influence each other's routing tables. Router A has a routing table with a bunch of entries. One of these entries is for 10.1.1.0/24 network, which we'll refer to as network X. Router A believes that the quickest path to network X is through its own interface 2, which is where router C is connected. Router A knows that sending data intended for network X through interface 2 to router C means it'll take 4 hops to get to the destination. Meanwhile, router B is only 2 hops removed from network X, and this is reflected in its routing table. Router B, using a distance vector protocol, sends the basic contents of its routing table to router A. Router A sees that network X is only 2 hops away from router B. Even with the extra hop to get from router A to router B, this means that network X is only 3 hops away from router A, if it forwards data to router B instead of router C. Armed with this new information, router A updates its routing table to reflect this. In order to reach network X in the fastest way, it should forward traffic through its own interface 1 to router B. Now, distance vector protocols are pretty simple, but they don't allow for a router to have much information about the state of the world outside of their own direct neighbors. Because of this, a router might be slow to react to a change in the network far away from it. This is why link state protocols were eventually invented. Routers using a link state protocol take a more sophisticated approach to determining the best path to a network. Link state protocols get their name because each router advertises the state of the link of each of its interfaces. These interfaces could be connected to other routers, or they could be direct connections to networks. The information about each router is propagated to every other router on the autonomous system. This means that every router on the system knows every detail about every other router in the system. Each router then uses this much larger set of information and runs complicated algorithms against it to determine what the best path to any destination network might be. Link state protocols require both more memory in order to hold all of this data and also much more processing power. This is because it has to run algorithms against this data in order to determine the quickest path to update the routing tables. As computer hardware has become more powerful and cheaper over the years, link state protocols have mostly made distance vector protocols outdated. Up next, we'll talk about exterior gateway protocols. See you there. Exterior gateway protocols are used to communicate data between routers representing the edges of an autonomous system. Since routers sharing data using interior gateway protocols are all under control of the same organization, routers use exterior gateway protocols when they need to share information across different organizations. Exterior gateway protocols are really key to the internet operating how it does today. So thanks, exterior gateway protocols. The internet is an enormous mesh of autonomous systems. At the highest levels, core internet routers need to know about autonomous systems in order to properly forward traffic. Since autonomous systems are known and defined collections of networks, getting data to the edge router of an autonomous system is the #1 goal of core internet routers. The IANA, or the Internet Assigned Numbers Authority, is a nonprofit organization that helps manage things like IP address allocation. The internet couldn't function without a single authority for these sorts of issues. Otherwise, anyone could try and use any IP space they wanted, which would cause total chaos online. Along with managing IP address allocation, the IANA is also responsible for ASN, or Autonomous System Number Allocation. ASNs are numbers assigned to individual autonomous systems. Just like IP addresses, ASNs are 32-bit numbers, but unlike IP addresses, they're normally referred to as just a single decimal number instead of being split out into readable bits. There are 2 reasons for this. First, IP addresses need to be able to represent a network ID portion and a host ID portion for each number. This is more easily accomplished by splitting the number in 4 sections of 8 bits, especially back in the day when address classes ruled the world. An ASN never needs to change in order for it to represent more networks or hosts. It's just the core internet routing tables that need to be updated to know what the ASN represents. Second, ASNs are looked at by humans far less often than IP addresses are. So, because it can be useful to be able to look at the IP 9.100.100.100 and know that 9.0.0.0/8 address space is owned by IBM, ASNs represent entire autonomous systems. Just being able to look up the fact that AS19604 belongs to IBM is enough. Unless you one day end up working at an internet service provider, understanding more details about how exterior gateway protocols work is out of scope for most people in IT. But grasping the basics of autonomous systems, ASNs, and how core internet routers route traffic between them is important to understand some of the basic building blocks of the internet. And now, a brief history lesson. Even as far back as 1996, it was obvious that the internet was growing at a rate that couldn't be sustained. When IP was first defined, it defined an IP address as a single 32-bit number. A single 32-bit number can represent 4,294,967,295 unique numbers, which definitely sounds like a lot. But as of 2017, there are an estimated 7.5 billion humans on Earth. This means that the IPv4 standard doesn't even have enough IP addresses available for every person on the planet. It also can't account for entire data centers filled with thousands and thousands of computers required for large-scale technology companies to operate. So, in 1996, RFC 1918 was published. RFC stands for Request for Comments. and is a long-standing way for those responsible for keeping the internet running to agree upon the standard requirements to do so. RFC 1918 outlined a number of networks that would be defined as non-routable address space. Non-routable address space is basically exactly what it sounds like. They are ranges of IPs set aside for use by anyone that cannot be routed to. Not every computer connected to the internet needs to be able to communicate with every other computer connected to the internet. Non-routable address space allows for nodes on such a network to communicate with each other, but no gateway router will attempt to forward traffic to this type of network. This might sound super limiting, and in some ways it is. In a future module, we'll cover a technology known as NAT, or Network Address Translation. It allows for computers on non-routable address space to communicate with other devices on the internet. But for now, let's just discuss non-routable address space in a vacuum. RFC 1918 defined 3 ranges of IP addresses that will never be routed anywhere by core routers. That means that they belong to no one and that anyone can use them. In fact, since they're separated from the way traffic moves across the internet, there's no limiting to how many people might use these addresses for their internal networks. The primary 3 ranges of non-routable address space are 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. These ranges are free for anyone to use for their internal networks. It should be called out that interior gateway protocols will route these address spaces, so they're appropriate for use within an autonomous system, but exterior gateway protocols will not. We've covered a lot in this module, and congratulations to you for sticking with it. Next up, we'll cover the transport and application layers. But first up, another quiz. You can do it, and remember, you can always go back and review the material as much as you need to.
So at one point I was working for a managed service provider, which is basically a company that provides IT support for other companies. And we were helping one of our clients migrate some of their systems onto a new version. And every time I tried to start one of their services, it would just error out and crash and kernel dump on the screen. And we couldn't figure out why. And eventually we get support for the third party that actually writes this piece of software on the line, and they can't figure it out, and it gets escalated and escalated, and eventually I have the personal phone number of the vice president at this company, who's the person who first wrote this software. And him and I spent several days trying to figure out what was going on, to no avail. We tried running this on different servers, we tried, everything we could possibly think of, until I realized that the license key that needed to be in place for the software to work had been copied over from a Windows machine onto a Linux machine, which means that the characters used at the end of a line to signal this line is over, please move on to the next one, were different. This software was choking on this different break line character. All I had to do was run one command and switch it over to a Linux file format, and everything worked. Also 2 weeks of my life lost, but we'll leave out exactly how long.
The first 3 layers of our network model have helped us describe how individual nodes on a network can communicate with other nodes on either their own network or a remote one. But we haven't discussed how individual computer programs can communicate with each other. It's time to dive into this, because that's really the aim of computer networking. We network computers together, not just so they can send data to each other, but because we want programs running on those computers to be able to send data to each other. This is where the transport and application layers of our networking model come into play. In short, the transport layer allows traffic to be directed to specific network applications, and the application layer allows these applications to communicate in a way they understand. By the end of this module, you'll be able to describe TCP ports and sockets and identify the different components of a TCP header. You'll also be able to show the difference between connection-oriented and connection-less protocols and explain how TCP is used to ensure data integrity. Are you ready to be transported to the next lesson? I hope so, because the transport layer is up next. See you there. The transport layer is responsible for lots of important functions of reliable computer networking. These include multiplexing and demultiplexing traffic, establishing long-running connections and ensuring data integrity through error checking and data verification. By the end of this lesson, you should be able to describe what multiplexing and demultiplexing are and how they work. You'll be able to identify the differences between TCP and UDP, explain the three-way handshake, and understand how TCP flags are used in this process. Finally, you'll be able to describe the basics of how firewalls keep networks safe. The transport layer has the ability to multiplex and demultiplex, which sets this layer apart from all others. Multiplexing in the transport layer means that nodes on a network have the ability to direct traffic toward many different receiving services. Demultiplexing is the same concept, just at the receiving end. It's taking traffic that's all aimed at the same node and delivering it to the proper receiving service. The transport layer handles multiplexing and demultiplexing through ports. A port is a 16-bit number that's used to direct traffic to specific services running on a networked computer. Remember the concept of server and clients? A server or service is a program running on a computer waiting to be asked for data. A client is another program that is requesting this data. Different network services run while listening on specific ports for incoming requests. For example, the traditional port for HTTP, or unencrypted web traffic, is port 80. If we want to request a web page from a web server running on a computer listening on IP 10.1.1.100, the traffic would be directed to port 80 on that computer. Ports are normally denoted with a colon after the IP address, so the full IP and port in this scenario could be described as 10.1.1.100:80. When written this way, it's known as a socket address or socket number. This same device might also be running in FTP, or File Transfer Protocol server. FTP is an older method used for transferring files from one computer to another, but you still see it in use today. FTP traditionally listens on port 21, so if you wanted to establish a connection to an FTP server running on the same IP that our example web server was running on, you direct traffic to 10.1.1.100 port 21. You might find yourself working in IT support at a small business. In these environments, a single server could host almost all of the applications needed to run a business. The same computer might host an internal website, the mail server for the company, a file server for sharing files, a print server for sharing network printers, pretty much anything. This is all possible because of multiplexing and demultiplexing, and the addition of ports to our addressing scheme. Heads up, in this video, we're going to dissect a TCP segment. In IT support, if network traffic isn't behaving as users expect it to, you might have to analyze it closely to troubleshoot. So get ready to take a peek at all the inner workings. Just like how an Ethernet frame encapsulates an IP datagram encapsulates a TCP segment. Remember that an Ethernet frame has a payload section, which is really just the entire contents of an IP datagram. Remember also that an IP datagram has a payload section, and this is made up of what's known as a TCP segment. A TCP segment is made up of a TCP header and a data section. This data section, as you might guess, is just another payload area for where the application layer places its data. A TCP header itself is split into lots of fields containing lots of information. First, we have the source port and the destination port fields. The destination port is the port of the service the traffic is intended for, which we talked about in the last video. A source port is a high-numbered port chosen from a special section of ports known as ephemeral ports. We'll cover ephemeral ports in more detail in a little bit. For now, it's enough to know that a source port is required to keep lots of outgoing connections separate. You know how a destination port, say port 80, is needed to make sure traffic reaches a web server running on a certain IP? Similarly, a source port is needed so that when the web server replies, the computer making the original request can send this data to the program that was actually requesting it. It is in this way that when a web server responds to your request to view a web page, that this response gets received by your web browser and not your word processor. Next up is a field known as the sequence number. This is a 32-bit number that's used to keep track of where in a sequence of TCP segments this one is expected to be. You might remember that lower on our protocol stack, there are limits to the total size of what we send across the wire. An Ethernet frame is usually limited in size to 1518 bytes, but we usually need to send way more data than that. At the transport layer, TCP splits all of this data up into many segments. The sequence number in a header is used to keep track of which segment out of many this particular segment might be. The next field, the acknowledgement number, is a lot like the sequence number. The acknowledgement number is the number of the next expected segment. In very simple language, a sequence number of 1 and an acknowledgement number of 2 could be read as this is segment 1, expect segment 2 next. The data offset field comes next. This field is a 4-bit number that communicates how long the TCP header for this segment is. This is so that the receiving network device understands where the actual data payload begins. Then we have 6 bits that are reserved for the 6 TCP control flags. We'll cover the control flags and what they each mean in the next video, so flag this for later. The next field is a 16-bit number known as the TCP window. A TCP window specifies the range of sequence numbers that might be sent before an acknowledgement is required. As we'll cover in more detail soon, TCP is a protocol that's super reliant on acknowledgements. This is done in order to make sure that all expected data is actually being received and that the sending device doesn't waste time sending data that isn't being received. The next field is a 16-bit checksum. It operates just like the checksum fields at the IP and Ethernet level. Once all of a segment has been ingested by a recipient, the checksum is calculated across the entire segment and is compared with the checksum in the header to make sure that there was no data lost or corrupted along the way. The urgent pointer field is used in conjunction with one of the TCP control flags to point out particular segments that might be more important than others. This is a feature of TCP that hasn't really ever seen adoption, and you'll probably never find it in modern networking. Even so, it's important to know what all sections of the TCP header are. Next up, we have the options field. Like the urgent pointer field, this is rarely used in the real world, but it's sometimes used for more complicated flow control protocols. Finally, we have some padding, which is just a sequence of zeros to ensure that the data payload section begins at the expected location. As a protocol, TCP establishes connections used to send long chains of segments of data. You can contrast this with the protocols that are lower in the networking model. These include IP and Ethernet, which just send individual packets of data. As an IT support specialist, you need to understand exactly how that works so you can troubleshoot issues where network traffic may not be behaving in the expected manner. The way TCP establishes a connection is through the use of different TCP control flags used in a very specific order. Before we cover how connections are established and closed, let's first define the 6 TCP control flags. We'll look at them in the order that they appear in a TCP header. Heads up, This isn't necessarily in the same order of how frequently they're set or how important they are. The first flag is known as URG. This is short for urgent. A value of 1 here indicates that the segment is considered urgent and that the urgent pointer field has more data about this. Like we mentioned in the last video, this feature of TCP has never really had widespread adoption and isn't normally seen. The second flag is ACK, short for acknowledged. A value of 1 in this field means that the acknowledgement number field should be examined. The third flag is PSH, which is short for push. This means that the transmitting device wants the receiving device to push currently buffered data to the application on the receiving end as soon as possible. A buffer is a computing technique where a certain amount of data is held somewhere before being sent somewhere else. This has lots of practical applications. In terms of TCP, it's used to send large chunks of data more efficiently. By keeping some amount of data in a buffer, TCP can deliver more meaningful chunks of data to the program waiting for it. But in some cases, you might be sending a very small amount of information that you need the listening program to respond to immediately. This is what the push flag does. The fourth flag is RST, short for reset. This means that one of the sides in a TCP connection hasn't been able to properly recover from a series of missing or malformed segments. It's a way for one of the partners in a TCP connection to basically say, wait, I can't put together what you mean. Let's start over from scratch. The fifth flag is SYN, which stands for synchronize. It's used when first establishing a TCP connection and makes sure the receiving end knows to examine the sequence number field. And finally, our sixth flag is FIN, which is short for finish. When this flag is set to 1, it means the transmitting computer doesn't have any more data to send and the connection can be closed. For a good example of how TCP control flags are used, let's check out how a TCP connection is established. Computer A will be our transmitting computer, and computer B will be our receiving computer. To start the process off, computer A sends a TCP segment to computer B with a SYN flag set. This is computer A's way of saying, let's establish a connection and look at my sequence number field so we know where this conversation starts. Computer B then responds with a TCP segment where both the SYN and ACK flags are set. This is computer B's way of saying, sure, let's establish a connection and I acknowledge your sequence number. Then computer A responds again with just the ACK flag set, which is just saying, I acknowledge your acknowledgement. Let's start sending data. I love how polite they are to each other. This exchange, involving segments that have SYN, SYN-ACK, and ACK set, happens every single time a TCP connection is established anywhere, and is so famous that it has a nickname, the three-way handshake. A handshake is a way for two devices to ensure that they're speaking the same protocol and will be able to understand each other. Once the three-way handshake is complete, the TCP connection is established. Now, computer A is free to send whatever data it wants to computer B, and vice versa. Since both sides have now sent SYN-ACK pairs to each other, a TCP connection in this state is operating in full duplex. Each segment sent in either direction should be responded to by a TCP segment with the ACK field set. This way, the other side always knows what has been received. Once one of the devices involved with the TCP connection is ready to close the connection, something known as a four-way handshake happens. The computer ready to close the connection sends a FIN flag, which the other computer acknowledges with an ACK flag. Then, if this computer is also ready to close the connection, which will almost always be the case, it will send a FIN flag. This is again responded to by an ACK flag. Hypothetically, a TCP connection can stay open in simplex mode with only one side closing the connection, but this isn't something you'll run into very often. Up next, I'll socket to you with information on TCP socket states. So many networking puns. Okay, see you there. A socket is the instantiation of an endpoint in a potential TCP connection. An instantiation is the actual implementation of something defined elsewhere. TCP sockets require actual programs to instantiate them. You can contrast this with a port, which is more of a virtual descriptive thing. In other words, you can send traffic to any port you want, but you're only going to get a response if a program has opened a socket on that port. TCP sockets can exist in lots of states, and being able to understand what those mean will help you troubleshoot network connectivity issues as an IT support specialist. We'll cover the most common ones here. Listen. Listen means that a TCP socket is ready and listening for incoming connections. You'd see this on the server side only. SYN sent. This means that a synchronization request has been sent, but the connection hasn't been established yet. You'd see this on the client side only. SYN received. This means that a socket previously in a listen state has received a synchronization request and sent a SYN ACK back, but it hasn't received the final ACK from the client yet. You'd see this on the server side only. Established. This means that the TCP connection is in working order and both sides are free to send each other data. You'd see this state on both the client and server sides of a connection. This will be true of all the following socket states too, so keep that in mind. FIN wait. This means that a FIN has been sent, but the corresponding ACK from the other end hasn't been received yet. Close wait. This means that the connection has been closed at the TCP layer, but that the application that opened the socket hasn't released its hold on the socket yet. Closed. This means that the connection has been fully terminated and that no further communication is possible. There are other TCP socket states that exist. Additionally, socket states and their names can vary from operating system to operating system. That's because they exist outside of the scope of the definition of TCP itself. TCP as a protocol is universal in how it's used, since every device speaking the TCP protocol has to do this in the exact same way for communications to be successful. Choosing how to describe the state of a socket at the operating system level isn't quite as universal. When troubleshooting issues at the TCP layer, make sure you check out the exact socket state definitions for the systems you're working with. So far, we've mostly focused on TCP, which is a connection-oriented protocol. A connection-oriented protocol is one that establishes a connection and uses this to ensure that all data has been properly transmitted. A connection at the transport layer implies that every segment of data sent is acknowledged. This way, both ends of the connection always know which bits of data have definitely been delivered to the other side and which haven't. Connection-oriented protocols are important because the internet is a vast and busy place, and lots of things could go wrong while trying to get data from point A to point B. You might remember from our lesson about the physical layer that even some minor crosstalk from a neighboring twisted pair in the same cable can be enough to make a cyclical redundancy check fail. This could cause the entire frame to be discarded. Yikes. If even a single bit doesn't get transmitted properly, the resulting data is often incomprehensible by the receiving end. And remember that at the lowest level, a bit is just an electrical signal within a certain voltage range. But there are plenty of other reasons why traffic might not reach its destination beyond line errors. It could be anything. Pure congestion might cause a router to drop your traffic in favor of forwarding more important traffic, or a construction company could cut a fiber cable connecting two ISPs. Anything's possible. Connection-oriented protocols, like TCP, protect against this by forming connections and through the constant stream of acknowledgements. Our protocols at lower levels of our network model, like IP and Ethernet, do use checksums to ensure that all the data they received was correct. But did you notice that we never discussed any attempts at resending data that doesn't pass this check? That's because that's entirely up to the transport layer protocol. At the IP or Ethernet level, if a checksum doesn't compute, all of that data is just discarded. It's up to TCP to determine when to resend this data. Since TCP expects an ACK for every bit of data it sends, it's in the best position to know what data successfully got delivered and can make the decision to resend a segment if needed. This is another reason why sequence numbers are so important. While TCP will generally send all segments in sequential order, they may not always arrive in that order. If some of the segments had to be resent due to errors at lower layers, it doesn't matter if they arrive slightly out of order. This is because sequence numbers allow for all of the data to be put back together in the right order. It's pretty handy. Now, as you might have picked up on, there's a lot of overhead with connection-oriented protocols like TCP. You have to establish the connection, you have to send a stream of constant streams of acknowledgements, you have to tear the connection down at the end. That all accounts for a lot of extra traffic. While this is important traffic, it's really only useful if you absolutely positively have to be sure your data reaches its destination. You can contrast this with connectionless protocols. The most common of these is known as UDP, or User Datagram Protocol. Unlike TCP, UDP doesn't rely on connections, and it doesn't even support the concept of an acknowledgement. With UDP, you just set a destination port and send the packet. This is useful for messages that aren't super important. A great example of UDP is streaming video. Let's imagine that each UDP datagram is a single frame of a video. For the best viewing experience, you might hope that every single frame makes it to the viewer, but it doesn't really matter if a few get lost along the way. A video will still be pretty watchable unless it's missing a lot of its frames. By getting rid of all the overhead of TCP, you might actually be able to send higher quality video with UDP. That's because you'll be saving more of the available bandwidth for actual data transfer instead of the overhead of establishing connections and acknowledging delivered data segments. You know what network device we haven't mentioned that you're probably super familiar with? A firewall. A firewall is just a device that blocks traffic that meets certain criteria. Firewalls are a critical concept to keeping a network secure, since they're the primary way you can stop traffic you don't want from entering a network. Firewalls can actually operate at lots of different layers of the network. There are firewalls that can perform inspection of application layer traffic, and firewalls that primarily deal with blocking ranges of IP addresses. The reason we cover firewalls here is that they're most commonly used at the transportation layer. Firewalls that operate at the transportation layer will generally have a configuration that enables them to block traffic to certain ports while allowing traffic to other ports. Let's imagine a simple small business network. This small business might have one server, which hosts multiple network services. This server might have a web server that hosts the company's website while also serving as the file server for a confidential internal document. A firewall placed at the perimeter of the network could be configured to allow anyone to send traffic to port 80 in order to view the web page. At the same time, it could block all access for external IPs to any other port so that no one outside of the local area network could access the file server. Firewalls are sometimes independent network devices, but it's really better to think of them as a program that can run anywhere. For many companies and almost all home users, the functionality of a router and a firewall is performed by the same device. And firewalls can run on individual hosts instead of being a network device. All major modern operating systems have firewall functionality built in. That way, blocking or allowing traffic to various ports, and therefore to specific services, can be performed at the host level as well. Up next, firing up your brain for a short quiz. Welcome to our lesson about the application layer. We're almost done covering all aspects of our networking model, which means you've already learned how computers process electrical or optical signals to send communication across a cable at the physical layer. We've also covered how individual computers can address each other and send each other data using Ethernet at the data link layer. We've discussed how the network layer is used by computers and routers to communicate between different networks using IP. And in our last lesson, we covered how the transportation layer ensures that data is received and sent by the proper applications. You're chock full of layers of new information. Now, we can finally talk about how those actual applications send and receive data using the application layer. Just like with every other layer, TCP segments have a generic data section to them. As you might have guessed, this payload section is actually the entire contents of whatever data applications want to send to each other. It could be contents of a web page if a web browser is connecting to a web server. This could be the streaming video content of your Netflix app on your PlayStation connecting to the Netflix servers. It could be the contents of a document your word processor is sending to a printer, and many more things. There are a lot of protocols used at the application layer, and they are numerous and diverse. At the data link layer, the most common protocol is Ethernet. I should call out that wireless technologies do use other protocols at this layer, which we'll cover in a future module. At the network layer, use of IP is everywhere you look. At the transport layer, TCP and UDP cover most of the use cases, but at the application layer, there are just so many different protocols in use, it wouldn't make sense for us to cover them. Even so, one concept you can take away about application layer protocols is that they're still standardized across application types. Let's dive a little deeper into web servers and web browsers for an example. There are lots of different web browsers. You could be using Chrome, Internet Explorer, Safari, you name it. They'll need to speak the protocol. The same thing is true for web servers. In this case, the web browser would be the client and the web server would be the server. The most popular web servers are Microsoft IIS, Apache, and Nginx, but they also need to all speak the same protocol. This way, you ensure that no matter which browser you're using, you'd still be able to speak to any server. For web traffic, the application layer protocol is known as HTTP. All of these different web browsers and web servers have to communicate using the same HTTP protocol specifications in order to ensure interoperability. The same is true for most other classes of application. You might have dozens of choices for an FTP client, but they all need to speak the FTP protocol in the same way. In our opening module, we talked about how there are lots of competing network layer models. We've been working from a 5-layer model, but you'll probably run into various other models during your career as an IT support specialist. Some models might combine the physical and data link layers into one and only talk about 4 layers. But you might remember a certain model we called out specifically in a reading section back in the first module. This is the OSI, or Open Systems Interconnection model. This model is important to understand with our 5-layer model because it's the most rigorously defined. That means it's often used in academic settings or by various network certification organizations. The OSI model has 7 layers and introduces 2 additional layers between our transport layer and our application layer. The 5th layer in the OSI model is the session layer. The concept of the session layer is that it's responsible for things like facilitating the communication between actual applications and the transport layer. It's the part of the operating system that takes the application layer data that's been unencapsulated from all of the layers below it and hands it off to the next layer in the OSI model, the presentation layer. The presentation layer is responsible for making sure that the unencapsulated application layer data is actually able to be understood by the application in question. This is the part of an operating system that might handle encryption or compression of data. While these are important concepts to keep in mind, you'll notice that there isn't any encapsulation going on. That's why in our model, we lump all of these functions into the application layer. We believe a 5-layer model is the most useful when it comes to the day-to-day business of understanding networking, but the 7-layer OSI model is also prevalent. No networking education would be complete without understanding its basics. Now that you know the basics of how every layer of our network model works, let's go through an exercise to look at how everything works at every step of the way. Spoiler alert, things are about to get a little geeky in a good way. Imagine 3 networks. Network A will contain address space 10.1.1.0/24. Network B will contain address space 192.168.1.0/24. And network C will be 172.16.1.0/24. Router A sits between network A and network B, with an interface configured with an IP of 10.1.1.1 on network A and an interface at 192.168.1.254 on network B. There's a second router, router B, which connects networks B and C. It has an interface on network B with an IP address of 192.168.1.1 and an interface on network C with an IP address of 172.16.1.1. Now, let's put a computer on one of the networks. Imagine it's a desktop sitting on someone's desk at their workplace. It'll be our client in this scenario, and we'll refer to it as computer 1. It's part of network A and has been assigned an IP address of 10.1.1.100. Now, let's put another computer on one of our other networks. This one is a server in a data center. It'll act as our server in this scenario, and we'll refer to it as computer 2. It's part of network C and has been assigned an IP address of 172.16.1.100 and has a web server listening on port 80. An end user sitting at computer 1 opens up a web browser and enters 172.16.1.100 into the address bar. Let's see what happens. The web browser running on computer 1 knows it's been ordered to retrieve a web page from 172.16.1.100. The web browser communicates with the local networking stack, which is the part of the operating system responsible for handling networking functions. The web browser explains that it's going to want to establish a TCP connection to 172.16.1.100 port 80. The networking stack will now examine its own subnet. It sees that it lives on the network 10.1.1.0/24, which means that the destination 172.16.1.100 is on another network. At this point, computer 1 knows that it'll have to send any data to its gateway for routing to a remote network, and it's been configured with a gateway of 10.1.1.1. Next, computer 1 looks at its ARP table to determine what MAC address of 10.1.1.1 is, but it doesn't find any corresponding entry. Uh-oh. It's okay. Computer A crafts an ARP request for an IP address of 10.1.1.1, which it sends to the hardware broadcast address of all Fs. This ARP discovery request is sent to every node on the local network. When router A receives this ARP message, it sees that it's the computer currently assigned the IP address of 10.1.1.1. So it responds to computer 1 to let it know about its own MAC address of 001122334455. Computer 1 receives this response and now knows the hardware address of its gateway. This means that it's ready to start constructing the outbound packet. Computer 1 knows that it's being asked by the web browser to form an outbound TCP connection, which means it'll need an outbound TCP port. The operating system identifies the ephemeral port of 50,000 as being available and opens a socket connecting the web browser to this port. Since this is a TCP connection, the networking stack knows that before it can actually transmit any of the data the web browser wants it to, it'll need to establish a connection. The networking stack starts to build a TCP segment. It fills in all the appropriate fields in the header, including a source port of 50,000 and a destination port of 80. A sequence number is chosen and is used to fill in the sequence number field. Finally, the SYN flag is set and a checksum for the segment is calculated and written to the checksum field. Our newly constructed TCP segment is now passed along to the IP layer of the networking stack. This layer constructs an IP header. This header is filled in with the source IP, the destination IP, and a TTL of 64, which is a pretty standard value for this field. Next, the TCP segment is inserted as the data payload for the IP datagram, and a checksum is calculated for the whole thing. Now that the IP datagram has been constructed, computer 1 needs to get this to its gateway, which it now knows has a MAC address of 001122334455. So an Ethernet frame is constructed. All the relevant fields are filled in with the appropriate data, most notably the source and destination MAC addresses. Finally, the IP datagram is inserted as the data payload of the Ethernet frame, and another checksum is calculated. Now we have an entire Ethernet frame ready to be sent across the physical layer. The network interface connected to computer 1 sends this binary data as modulations of the voltage of an electrical current running across a Cat6 cable that's connected between it and a network switch. This switch receives the frame and inspects the destination MAC address. The switch knows which of its interfaces this MAC address is attached to and forwards the frame across only the cable connected to this interface. At the other end of this link is router A, which receives the frame and recognizes its own hardware address as the destination. Router A knows that this frame is intended for itself, so it now takes the entirety of the frame and calculates a checksum against it. Router A compares this checksum with the one in the Ethernet frame header and sees that they match, meaning all of the data has made it in one piece. Next, router A strips away the Ethernet frame, leaving it with just the IP datagram. Again, it performs a checksum calculation against the entire datagram, and again, it finds that it matches, meaning all the data is correct. It inspects the destination IP address and performs a lookup of this destination in its routing table. Router A sees that in order to get data to the 172.16.1.0/24 network, the quickest path is one hop away via router B, which has an IP of 192.168.1.1. Router A looks at all the data in the IP datagram, decrements the TTL by 1, calculates a new checksum reflecting the new TTL value, and makes a new IP datagram with this data. Router A knows that it needs to get this datagram to router B, which has an IP address of 192.168.1.1. It looks at its ARP table and sees that it has an entry for 192.168.1.1. Now, router A can begin to construct an Ethernet frame with the MAC address of its interface on network B as the source and the MAC address of router B's interface on network B as the destination. Once the values for all fields in this frame have been filled out, router A places the newly constructed IP datagram into the data payload field, calculates a checksum, and places this checksum into place, and sends the frame out to network B. Just like before, this frame makes it across network B and is received by router B. Router B performs all the same checks, removes the Ethernet frame encapsulation, and performs a checksum against the IP datagram. It then examines the destination IP address. Looking at its routing table, router B sees that the destination address of computer 2, or 172.16.1.100, is on a locally connected network. So it decrements the TTL by 1 again, calculates a new checksum, and creates a new IP datagram. This new IP datagram is again encapsulated by a new Ethernet frame, this one with the source and destination MAC address of router B and computer 2. And the whole process is repeated one last time. The frame is sent out onto network C. A switch ensures it gets sent out of the interface that computer 2 is connected to. Computer 2 receives the frame, identifies its own MAC address as the destination, and knows that it's intended for itself. Computer 2 then strips away the Ethernet frame, leaving it with the IP datagram. It performs a CRC and recognizes that the data has been delivered intact. It then examines the destination IP address and recognizes that as its own. Next, computer 2 strips away the IP datagram, leaving it with just the TCP segment. Again, the checksum for this layer is examined and everything checks out. Next, computer 2 examines the destination port, which is 80. The networking stack on computer 2 checks to ensure that there's an open socket on port 80, which there is. It's in the listen state and held open by a running Apache web server. Computer 2 then sees that this packet has the SYN flag set. So it examines the sequence number and stores that, since it'll need to put the sequence number in the acknowledgement field once it crafts the response. After all of that, all we've done is get a single TCP segment containing a SYN flag from one computer to a second one. Everything would have to happen all over again for computer 2 to send a SYN ACK response to computer 1. Then everything would have to happen all over again for computer 1 to send an ACK back to computer 2, and so on and so on. Looking at all of this end to end hopefully helps show how all the different layers of our networking model have to work together to get the job done. I hope it also gives you some perspective in understanding how remarkable computer networking truly is. Even more remarkable than that, you for making it through this module. Now it's time to apply your new knowledge to the next assessment. When you're done, I'll see you in the next video. But first, another quiz. You got this. But even if you don't, just review the material until you get more comfortable with this stuff. There's no denying it. Computer networking is a complicated business that involves many technologies, layers, and protocols. At the end of the day, the main purpose of computer networking is so network services can be available to answer requests for the data from clients. The sheer number and variety of things that might comprise a network service makes it impossible to cover all of them. But there are a lot of network services and technologies that are used to help make computer networking more user-friendly and secure. These network services and technologies are ones that directly relate to the business of networking itself, and it's important to understand how those work. If something on the network isn't working as expected, the first place you should look at are the services we'll be covering here. And being asked to fix things that aren't working as expected will be a major part of being an IT support specialist. By the end of this module, you'll be able to describe why name resolution is important, identify the many steps involved with DNS lookup, and understand the most common DNS record types. You'll also be able to explain how DHCP makes network administration a simpler task. You'll be able to demonstrate how NAT technologies help keep networks secure and help preserve precious IP address space. Finally, you'll be able to describe how VPNs and proxies help users get connected and stay secure. As you can see, we've got a lot to tackle, so let's get started. Computers speak to each other in numbers. At the very lowest levels, all computers really understand are 1 and 0. Reading binary numbers isn't the easiest for humans, so most binary numbers are represented in lots of different forms. This is especially true in the realm of networking. Remember that an IP address is really just a 32-bit binary number, but it's normally written out as 4 octets in decimal form, since that's easier for humans to read. You might also remember that MAC addresses are just 48-bit binary numbers that are normally written out in 6 groupings of 2 hexadecimal digits each. While remembering 192.168.1.100 might be easier than remembering a long string of ones and zeros, it still doesn't do a very good job when you have to remember more than just a few addresses. Imagine having to remember the 4 octets of an IP address for every website you visit. It's just not a thing that the human brain is normally good at. Humans are much better at remembering words. That's where DNS, or Domain Name System, comes into play. DNS is a global and highly distributed network service that resolves strings of letters into IP addresses for you. Let's say you wanted to check a weather website to see what the temperature is going to be like. It's much easier to type www.weather.com into a web browser than it is to remember that one of the IP addresses for this site is 184.29.131.121. The IP address for a domain name can also change all the time for a lot of different reasons. A domain name is just the term we use for something that can be resolved by DNS. In the example we just used, www.weather.com would be the domain name, and the IP it resolves to could change depending on a variety of factors. Let's say that weather.com was moving their web server to a new data center. Maybe they've signed a new contract, or the old data center was shutting down. By using DNS, an organization can just change what IP a domain name resolves to, and the end user would never even know. So not only does DNS make it easier for humans to remember how to get to a website, it also lets administrative changes happen behind the scenes without an end user having to change their behavior. Try to imagine a world where you'd have to remember every IP for every website you visit, while also having to memorize new ones if something changed. We'd spend our whole day memorizing numbers. The importance of DNS for how the internet operates today can't be overstated. IP addresses might resolve to different things depending on where in the world you are. While most internet communications travel at the speed of light, the further you have to route data, the slower things will become. In almost all situations, it's going to be quicker to transmit a certain amount of data between places that are geographically close to each other. If you're a global web company, you'd want people from all over the world to have a great experience accessing your website. So instead of keeping all of your web servers in one place, you could distribute them across data centers across the globe. This way, someone in New York visiting a website might get served by a web server close to New York, while someone in New Delhi might get served by a web server close to New Delhi. Again, DNS helps provide this functionality. Because of its global structure, DNS lets organizations decide if you're in the region, resolve the domain name to this IP. If you're in this other region, resolve this domain to this other IP. DNS serves lots of purposes and might be one of the most important technologies to understand as an IT support specialist, so you can effectively troubleshoot networking issues. At its most basic, DNS is a system that converts domain names into IP addresses. It's the way humans are likely to remember and categorize things resolved into the way computers prefer to think of things. This process of using DNS to turn a domain name into an IP address is known as name resolution. Let's take a closer look at exactly how this works. The first thing that's important to know is that DNS servers are one of the things that need to be specifically configured at a node on a network. For a computer to operate on a modern network, they need to have a certain number of things configured. Remember that MAC addresses are hard-coded and tied to specific pieces of hardware. But we've also covered that the IP address, subnet mask, and gateway for a host must be specifically configured. A DNS server is the fourth and final part of the standard modern network configuration. These are almost always the four things that must be configured for a host to operate on a network in an expected way. I should call out that a computer can operate just fine without DNS, or without a DNS server being configured. But as we covered in the last video, this makes things difficult for any human that might be using that computer. There are 5 primary types of DNS servers: caching name servers, recursive name servers, root name servers, TLD name servers, and authoritative name servers. As we dive deeper into these, it's important to note that any given DNS server can fulfill many of these roles at once. Caching and recursive name servers are generally provided by an ISP or your local network. Their purpose is to store domain name lookups for a certain amount of time. As you'll see in a moment, there are lots of steps in order to perform a fully qualified resolution of a domain name. In order to prevent this from happening every single time a new TCP connection is established, your ISP or local network will generally have a caching name server available. Most caching name servers are also recursive name servers. Recursive name servers are ones that perform full DNS resolution requests. In most cases, your local name server will perform the duties of both but it's definitely possible for a name server to be either just caching or just recursive. Let's introduce an example to better explain how this works. You and your friend are both connected to the same network, and you both want to check out facebook.com. Your friend enters www.facebook.com into a web browser, which means that their computer now needs to know the IP of www.facebook.com in order to establish a connection. Both of your computers are on the same network, which usually means that they've both been configured with the same name server. So your friend's computer asks the name server for the IP of www.facebook.com, which it doesn't know. This name server now performs a fully recursive resolution to discover the correct IP for www.facebook.com. This involves a bunch of steps we'll cover in just a moment. This IP is then both delivered to your friend's computer and stored locally in a cache. A few minutes later, you enter www.facebook.com into a web browser. Again, your computer needs to know the IP for this domain, so your computer asks the local name server it's been configured with, which is the same one your friend's computer was just talking to. Since the domain name www.facebook.com had just been looked up, the local name server still has the IP that it resolved to stored, and is able to deliver that back to your computer without having to perform a full lookup. This is how the same servers act as a caching server. All domain names in the global DNS system have a TTL, or time to live. This is a value in seconds that can be configured by the owner of a domain name for how long a name server is allowed to cache an entry before it should discard it and perform a full resolution again. Several years ago, it was normal for these TTLs to be really long, sometimes a full day or more. This is because the general bandwidth available on the internet was just much less, so network administrators didn't want to waste what bandwidth was available to them by constantly performing full DNS lookups. As the internet has grown and gotten faster, these TTLs for most domains have dropped to anywhere from a few minutes to a few hours, but it's important to know that sometimes you still run into domain names with very lengthy TTLs. It means that it can take up to the length of a total TTL for a change in DNS record to be known to the entire internet. Now, let's look at what happens when your local recursive server needs to perform a full recursive resolution. The first step is always to contact a root name server. There are 13 total root name servers, and they're responsible for directing queries toward the appropriate TLD name server. In the past, these 13 root servers were distributed to very specific geographic regions, but today they're mostly distributed across the globe via Anycast. Anycast is a technique that's used to route traffic to different destinations depending on factors like location, congestion, or link health. Using Anycast, a computer can send a datagram to a specific IP, but could see it routed to one of many different actual destinations depending on a few factors. This should also make it clear that there aren't really only 13 physical root name servers anymore. It's better to think of them as 13 authorities that provide root name lookups as a service. The root servers will respond to a DNS lookup with the TLD name server that should be queried. TLD stands for top level domain and represents the top of the hierarchical DNS name resolution system. A TLD is the last part of any domain name. Using www.facebook.com as an example again, the .com portion should be thought of as the TLD. We'll go into more details about the different components of a domain name in an upcoming lesson. For each TLD in existence, there's a TLD name server. But just like with root servers, this doesn't mean there's only physically one server in question. It's most likely a global distribution of Anycast accessible servers responsible for each TLD. The TLD name servers will respond again with a redirect, this time informing the computer performing the name lookup with what authoritative name server to contact. Authoritative name servers are responsible for the last two parts of any domain name, which is the resolution at which a single organization may be responsible for DNS lookups. Using www.weather.com as an example, the TLD name server would point a lookup at the authoritative server for weather.com, which would likely be controlled by the Weather Channel, the organization itself that runs the site. Finally, the DNS lookup could be redirected at the authoritative server for weather.com, which would finally provide the actual IP of the server in question. This strict hierarchy is very important to the stability of the internet, making sure that all full DNS resolutions go through a strictly regulated and controlled series of lookups to get the correct responses is the best way to protect against malicious parties redirecting traffic. Your computer will blindly send traffic to whatever IP it's told to. So by using a hierarchical system controlled by trusted entities in the way DNS does, we can better ensure that the responses to DNS lookups are accurate. Now that you see how many steps are involved, it should make sense why we trust our local name servers to cache DNS lookups. It's so that full lookup path doesn't have to happen for every single TCP connection. In fact, your local computer, from your phone to a desktop, will generally have its own temporary DNS cache as well. That way, it doesn't have to bother its local name server for every TCP connection either. DNS is a great example of an application layer service that uses UDP for the transport layer instead of TCP. This can be broken down into a few simple reasons. Remember that the biggest difference between TCP and UDP is that UDP is connectionless. This means there's no setup or teardown of a connection, so much less traffic needs to be transmitted overall. A single DNS request and its response can usually fit inside of a single UDP datagram, making it an ideal candidate for a connectionless protocol. It's also worth calling out that DNS can generate a lot of traffic. It's true that caches of DNS entries are stored both on local machines and caching name servers. But it's also true that if the full resolution needs to be processed, we're talking about a lot more traffic. Let's see what it would look like for a full DNS lookup to take place via TCP. First, the host that's making the DNS resolution request would send a SYN packet to the local name server on port 53, which is the port that DNS listens on. This name server would then need to respond with a SYN-ACK packet. That means the original host would have to respond with an ACK in order to complete the three-way handshake. That's 3 packets. Now that the connection has been established, the original host would have to send the actual request. I'd like the IP address for foo.com, please. When it receives this request, the name server would have to respond with another ACK. I got your request for foo.com. We're up to 5 packets sent now. In our scenario, the first caching name server doesn't have anything cached for foo.com, so it needs to talk to a root name server to find out who's responsible for the .com TLD. This would require a 3-way handshake: the actual request, the ACK of the request, the response, and then the ACK of the response. Oof. Finally, the connection would have to be closed via a 4-way handshake. That's 11 more packets, or 16 total. Now that the recursive name server has the correct TLD name server, it needs to repeat that entire process to discover the proper authoritative name server. That's 11 more packets, bringing us up to 27 so far. Finally, the recursive name server would have to repeat the entire process one more time while talking to the authoritative name server in order to actually get the IP of foo.com. This is 11 more packets for a running total of 38. Now that the local name server finally has the IP address of foo.com, it can finally respond to the initial request. It responds to the DNS resolver that originally made the request, and then this computer sends an ACK back to confirm that it received the response. That's 2 more packets, putting us at 40. Finally, the TCP connection needs to be closed via a 4-way handshake. This brings us to a grand total of 44 packets at the minimum in order for a fully recursive DNS request to be fulfilled via TCP. 44 packets isn't really a huge number in terms of how fast modern networks operate, but it adds up fast, as you can see. Remember that DNS traffic is just a precursor to actual traffic. A computer almost always performs a DNS lookup because it needs to know the IP of a domain name in order to send it additional data, not just because it's curious. Now, let's check out how this would look with UDP. Spoiler alert, it doesn't take as many packets. The original computer sends a UDP packet to its local name server on port 53, asking for the IP for foo.com. That's one packet. The local name server acts as a recursive server and sends up a UDP packet to the root server, which sends a response containing the proper TLD name server. That's 3 packets. The recursive name server sends a packet to the TLD server and receives back a response containing the correct authoritative server. We're now at 5 packets. Next, the recursive name server sends its final request to the authoritative name server, which sends a response containing the IP for foo.com. That's 7 packets. Finally, the local name server responds to the DNS resolver that made the request in the first place with the IP for foo.com. That brings us to a grand total of 8 packets. See, way less packets. You can see now how much overhead TCP really requires. And for something as simple as DNS, it's just not needed. It's the perfect example for why protocols like UDP exist in addition to the more robust TCP. You might be wondering how error recovery plays into this, since UDP doesn't have any. The answer is pretty simple. The DNS resolver just asks again if it doesn't get a response. Basically, the same functionality that TCP provides at the transport layer is provided by DNS at the application layer in the most simple manner. A DNS server never needs to care about doing anything but responding to incoming lookups. And a DNS resolver simply needs to perform lookups and repeat them if they don't succeed. A real showcase of the simplicity of both DNS and UDP. I should call out that DNS over TCP does in fact exist and is also in use all over. As the web has gotten more complex, it's no longer the case that all DNS lookup responses can fit in a single UDP datagram. In these situations, a DNS name server would respond with a packet explaining that the response is too large. The DNS client would then establish a TCP connection in order to perform the lookup.
When you're working in IT, you work with a bunch of different systems. It could be, servers, databases, a bunch of flavor of operating systems. And then as a network engineer, you have to know how all those things work together. I think personally for me, growing up, I had a learning disorder. So I never felt like academics was a strong suit for me. So I felt like if I ever wanted to do computers or programming or networking, I had to be a genius, I had to be good at math and science, had to get straight A's. But for me, I realized that this wasn't about level of intelligence, it was more about your passion and how driven you were to learn. You don't have to be a genius, you just have to be driven and be able to teach yourself things and advance yourself. The best advice I got from a mentor was, maximize your potential. And I think that can be applied in all areas of life, but especially in IT and any career in technology, because you're never probably going to be the smartest person in the room. It's going to be about your path and your career, and just worry about that part of it. I don't think formal education is necessary for a role in IT. There's many paths to get there, and many different people take different paths. If someone is nervous that they don't have a 4-year degree or certain credentials, it's okay. IT is a place where if you know the information and you know your foundations, you're going to be able to achieve that career success you want. I just think when you look at the role that technology is playing in our daily lives, it just makes sense. And personally for me, I love solving problems. I like being challenged, and technology gives you all those challenges and those puzzles to solve. So I always tell people that doing IT as your starting ground is the foundation to whatever you want to start next. It's an umbrella of technologies, and you can try a bunch of different things and then slowly start to move into more of a specialization if you'd like to.
Remember, DNS is one of the most important technologies that an IT support specialist needs to know in order to troubleshoot networking issues. So let's get into the nitty-gritty. DNS in practice operates with a set of defined resource record types. These allow for different kinds of DNS resolutions to take place. There are dozens of different resource record types defined, but a lot of them only serve very specialized purposes. We'll cover the most basic ones here. The most common resource record is known as an A record. An A record is used to point a certain domain name at a certain IPv4 IP address. In our earlier discussions of DNS, we made the assumption that the DNS resolver was asking for the A record for a domain name. In its most basic use, a single A record is configured for a single domain name. But a single domain name can have multiple A records too. This allows for a technique known as DNS round robin to be used to balance traffic across multiple IPs. Round robin is a concept that involves iterating over a list of items one by one in an orderly fashion. The hope is that this ensures a fairly equal balance of each entry on the list that's selected. Let's say we're in charge of a domain name, www.microsoft.com. Microsoft is a large company and their website likely sees a lot of traffic. To help balance this traffic across multiple servers, we configure 4 A records for www.microsoft.com at the authoritative name server for the Microsoft.com domain. We'll use the IPs 10.1.1.1, 10.1.1.2, 10.1.1.3, and 10.1.1.4. When a DNS resolver performs a lookup of www.microsoft.com, all 4 IPs would be returned in the order first configured. 10.1.1.1, followed by 10.1.1.2, followed by 10.1.1.3, and finally 10.1.1.4. The DNS resolving computer would know that it should try to use the first entry, 10.1.1.1. But it knows about all 4, just in case a connection to 10.1.1.1 fails. The next computer to perform a lookup for www.microsoft.com would also receive all 4 IPs in the response, but the ordering will have changed. The first entry would be 10.1.1.2, followed by 10.1.1.3, followed by 10.1.1.4, and finally 10.1.1.1 would be last on that list. This pattern would continue for every DNS resolution attempt, cycling through all of the A records configured and balancing the traffic across these IPs. That's the basics of how DNS round-robin logic works. Another resource record type that's becoming more and more popular is the quad A record. A quad A record is very similar to an A record, except that it returns an IPv6 address instead of an IPv4 address. We'll cover the details of IPv6 in a future module. The CNAME record is also super common. A CNAME record is used to redirect traffic from one domain to another. Let's say that Microsoft runs their web servers at www.microsoft.com. They also want to make sure that anyone that enters just Microsoft.com into their web browser will get properly redirected. By configuring a CNAME record for Microsoft.com that resolves to www.microsoft.com, the resolving client would then know to perform another resolution attempt, this time for www.microsoft.com, and then use the IP returned by that second attempt. CNAMEs are really useful because they ensure you only have to change the canonical IP address of a server in one place. In fact, CNAME is just shorthand for canonical name. If we look again at our original example of making sure that visitors to both Microsoft.com and www.microsoft.com get to the same place, we could do this in 2 ways. We could set up identical A records for both Microsoft.com and www.microsoft.com domain names, and this would work just fine. But if the underlying IP address ever changes, we need to change it in 2 places, the A records for both Microsoft.com and www.microsoft.com. By setting up a CNAME that points Microsoft.com at www.microsoft.com, you'd only have to change the A record for www.microsoft.com. And you'd know that clients pointing at either domain would get the new IP address. This might not seem like a huge deal with just 2 records to worry about, but large companies with complex presences on the web might have dozens of these kinds of redirections. It's always easier to only have one source of truth. Another important resource record type is the MX record. MX stands for mail exchange, And this resource record is used in order to deliver email to the correct server. Many companies run their web and mail servers on different machines with different IPs. So the MX record makes it easy to ensure that email gets delivered to a company's mail server while other traffic, like web traffic, would get delivered to their web server. A record type very similar to the MX record is the SRV record. SRV stands for service record, and it's used to define the location of various specific services. It serves the exact same purpose as the MX resource record type, except for one thing. While MX is only for mail services, an SRV record can be defined to return the specifics of many different service types. For example, SRV records are often used to return the records of services like CalDAV, which is a calendar and scheduling service. The text record type is an interesting one. TXT stands for text and was originally intended to be used only for associating some descriptive text with a domain name for human consumption. The idea was that you could leave notes or messages that humans could discover and read to learn more about arbitrary specifics of your network. But over the years, as the internet and services that run on it have become more and more complex, the text record has been increasingly used to convey additional data intended for other computers to process. Since the text record has a field that's entirely free-form, clever engineers have figured out ways to use it to communicate data not originally intended to be communicated by a system like DNS. It's pretty clever, right? This text record is often used to communicate configuration preferences about network services that you've entrusted other organizations to handle for your domain. For example, it's common for the text record to be used to convey additional info to an email as a service provider, which is a company that handles your email delivery for you. There are lots of other DNS resource record types in common use, like the NS or SOA records, which are used to define authoritative information about DNS zones. We'll cover DNS zones in more detail in a future video, so stay tuned. Any given domain name has three primary parts, and they all serve specific purposes. Let's take the domain name www.google.com. The three parts here should be pretty easy to spot since they're each set off from each other by a period. They're www, Google, and com. The last part of a domain name is known as the TLD, or top-level domain. In this case, it's the .com portion of the domain name. There are only a certain restricted number of defined TLDs available, although that number has been growing a lot in recent years. The most common TLDs are ones you've probably already familiar with: .com, .net, .edu, and so on. You've probably also seen some country-specific TLDs, such as .de for Germany or .cn for China. Due to the growth of the internet, many of the TLDs originally defined have become very crowded. So today, a number of vanity TLDs are available, everything from .museum to .pizza. Administration and definition of TLDs is handled by a nonprofit organization known as ICANN, or the Internet Corporation for Assigned Names and Numbers, and I can tell you what they do. ICANN is a sister organization to the IANA, and together they help define and control both the global IP spaces along with the global DNS system. A domain is the name commonly used to refer to the second part of a domain name, which would be Google in our example. Domains are used to demarcate where control moves from a TLD name server to an authoritative name server. This is typically under the control of an independent organization or someone outside of ICANN. Domains can be registered and chosen by any individual or company, but they must all end in one of the predefined TLDs. The www portion of this is known as the subdomain, sometimes referred to as a host name if it's been assigned to only one host. When you combine all these parts together, you have what's known as a fully qualified domain name, or FQDN. While it costs money to officially register a domain with a registrar, subdomains can be freely chosen and assigned by anyone who controls such a registered domain. A registrar is just a company that has an agreement with ICANN to sell unregistered domain names. We'll talk more about dealing with registrars in a future module. Technically, you can have lots of subdomain names. For example, host.sub.sub.subdomain.domain.com could be completely valid, although you rarely see fully qualified domain names with that many levels. DNS can technically support up to 127 levels of domain in total for a single fully qualified domain name. There are some other restrictions in place for how a domain name can be specified. Each individual section can only be 63 characters long, and a complete FQDN is limited to a total of 255 characters. We've covered how authoritative name servers are responsible for responding to name resolution requests for specific domains, but they do more than that. An authoritative name server is actually responsible for a specific DNS zone. DNS zones are a hierarchical concept. The root name servers we covered earlier are responsible for the root zone. Each TLD name server is responsible for the zone covering its specific TLD. And what we refer to as authoritative name servers are responsible for some even finer grained zones underneath that. The root and TLD name servers are actually just authoritative name servers too. It's just that the zones that they're authoritative for are special cases. I should call out that zones don't overlap. For example, the administrative authority of the TLD name server for the .com TLD doesn't encompass the google.com domain. Instead, it ends at the authoritative server responsible for google.com. The purpose of DNS zones is to allow for easier control over multiple levels of a domain. As the number of resource records in a single domain increases, it becomes more of a headache to manage them all. Network administrators can ease this pain by splitting up their configurations into multiple zones. Let's imagine a large company that owns the domain largecompany.com. This company has offices in Los Angeles, Paris, and Shanghai. Very cosmopolitan. Let's say each office has around 200 people with their own uniquely named desktop computer. This would be 600 A records to keep track of if it was all configured as a single zone. What the company could do instead is split up each office into their own zone. So now we could have la.largecompany.com, pa.largecompany.com, and sh.largecompany.com as subdomains, each with their own DNS zone. A total of 4 authoritative name servers would now be required for the setup, one for largecompany.com and one for each of the subdomains. Zones are configured through what are known as zone files, simple configuration files that declare all resource records for a particular zone. So a zone file has to contain an SOA, or a start of authority, resource record declaration. This SOA record declares the zone and the name of the name server that is authoritative for it. Along with the SOA record, you'll usually find NS records, which indicate other name servers that might also be responsible for this zone. For simplicity's sake, we've been referring to server in the singular when discussing what's responsible for a zone, whether at the root, TLD, or domain level. But there are often going to be multiple physical servers with their own FQDNs and IP addresses involved. Having multiple servers in place for something as important as DNS is pretty common. Why? Well, if one server were to have a problem or suffer a hardware failure, you could always rely on one of the other ones to serve DNS traffic. Besides SOA and NS records, you'll also find some or all of the other resource record types we've already covered, like A, Quad A, and CNAME records, along with configurations such as default TTL values for the records served by this zone. Just like how subdomains can go many, many layers deep, zones can be configured to do this too. But just like with subdomains, it's rare to see zones deeper than just a few levels. Sometimes, you'll also see what are known as reverse lookup zone files. These let DNS resolvers ask for an IP and get the FQDN associated with it returned. These files are the same as zone files, except instead of A and quad A records, which resolve names to IPs, you'll find mostly pointer resource record declarations. As you might have guessed, a PTR, or pointer record, resolves an IP to a name. Up next, a dynamic quiz for you before a dynamic new lesson on dynamic host configuration protocol. See you there. Managing hosts on a network can be a daunting and time-consuming task. Every single computer on a modern TCP/IP-based network needs to have at least 4 things specifically configured: an IP address, the subnet mask for the local network, a primary gateway, and a name server. On their own, these 4 things don't seem like much, but when you have to configure them on hundreds of machines, it becomes super tedious. Out of these 4 things, 3 are likely the same on just about every node on the network: the subnet mask, the primary gateway, and DNS server. But the last item, an IP address, needs to be different on every single node on the network. That could require a lot of tricky configuration work, and this is where DHCP, or Dynamic Host Configuration Protocol, comes into play. Listen up, because DHCP is critical to know as an IT support specialist when it comes to troubleshooting networks. DHCP is an application layer protocol that automates the configuration process of hosts on a network. With DHCP, a machine can query a DHCP server when the computer connects to the network and receive all the networking configuration in one go. Not only does DHCP reduce the administrative overhead of having to configure lots of network devices on a single network, it also helps address the problem of having to choose what IP to assign to what machine. Every computer on a network requires an IP for communications, but very few of them require an IP that would be commonly known. For servers or network equipment on your network, like your gateway router, a static and known IP address is pretty important. For example, the devices on a network need to know the IP of their gateway at all times. If the local DNS server was malfunctioning, network administrators would still need a way to connect to some of these devices through their IP. Without a static IP configured for a DNS server, it would be hard to connect to it to diagnose any problems if it was malfunctioning. But for a bunch of client devices like desktops or laptops or even mobile phones, it's really only important that they have an IP on the right network. It's much less important exactly which IP that is. Using DHCP, you can configure a range of IP addresses that's set aside for these client devices. This ensures that any of these devices can obtain an IP address when they need one, but solves the problem of having to maintain a list of every node on the network and its corresponding IP. There are a few standard ways that DHCP can operate. DHCP, dynamic allocation, is the most common, and it works how we described it just now. A range of IP addresses is set aside for client devices, and one of these IPs is issued to these devices when they request one. Under a dynamic allocation, the IP of a computer could be different almost every time it connects to the network. Automatic allocation is very similar to dynamic allocation in that a range of IP addresses is set aside for assignment purposes. The main difference here is that the DHCP server is asked to keep track of which IPs it's assigned to certain devices in the past. Using this information, the DHCP server will assign the same IP to the same machine each time if possible. Finally, there's what's known as fixed allocation. Fixed allocation requires a manually specified list of MAC address and their corresponding IPs. When a computer requests an IP, the DHCP server looks for its MAC address in a table and assigns the IP that corresponds to that MAC address. If the MAC address isn't found, the DHCP server might fall back to automatic or dynamic allocation, or it might refuse to assign an IP altogether. This can be used as a security measure to ensure that only devices that have had their MAC address specifically configured at the DHCP server will ever be able to obtain an IP and communicate on the network. It's worth calling out that DHCP discovery can be used to configure lots of things beyond what we've touched on here. Along with things like IP address and primary gateway, you could also use DHCP to assign things like NTP servers. NTP stands for Network Time Protocol and is used to keep all computers on a network synchronized in time. We'll cover it in more detail in later courses, but for now, it's just worth knowing that DHCP can be used for more than just IP, subnet mask, gateway, and DNS server. DHCP is an application layer protocol, which means it relies on the transport, network, data link, and physical layers to operate. But you might have noticed that the entire point of DHCP is to help configure the network layer itself. Let's take a look at exactly how DHCP works and how it accomplishes communications without a network layer configuration in place. Warning, geeky stuff ahead. The process by which a client configured to use DHCP attempts to get network configuration information is known as DHCP discovery. The DHCP discovery process has 4 steps. First, we have the server discovery step. The DHCP client sends what's known as a DHCP discover message out onto the network. Since the machine doesn't have an IP and it doesn't know the IP of the DHCP server, a specially crafted broadcast message is formed instead. DHCP listens on UDP port 67, and DHCP discovery messages are always sent from UDP port 68. So the DHCP discover message is encapsulated in a UDP datagram with a destination port of 67 and a source port of 68. This is then encapsulated inside of an IP datagram with a destination IP of 255.255.255.255 and a source IP of 0.0.0.0. This broadcast message would get delivered to every node on the local area network, and if a DHCP server is present, it would receive this message. Next, the DHCP server would examine its own configuration and would make a decision on what, if any, IP address to offer to the client. This will depend on if it's configured to run with dynamic, automatic, or fixed address allocation. The response would be sent as a DHCP offer message with a destination port of 68, a source port of 67, a destination broadcast IP of 255.255.255.255, and its actual IP as the source. Since the DHCP offer is also a broadcast, it would reach every machine on the network. The original client would recognize that this message was intended for itself. This is because the DHCP offer has the field that specifies the MAC address of the client that sent the DHCP discover message. The client machine would now process this DHCP offer to see what IP is being offered to it. Technically, a DHCP client could reject this offer. It's totally possible for multiple DHCP servers to be running on the same network and for a DHCP client to be configured to only respond to an offer of an IP within a certain range, but this is rare. More often, the DHCP client would respond to the DHCP offer message with a DHCP request message. This message essentially says, yes, I would like to have an IP that you offered to me. Since the IP hasn't been assigned yet, this is again sent from an IP of 0.0.0.0 and to the broadcast IP of 255.255.255.255. Finally, the DHCP server receives the DHCP request message and responds with a DHCP ACK or DHCP acknowledgement message. This message is again sent to a broadcast IP of 255.255.255.255 and with a source IP corresponding to the actual IP of the DHCP server. Again, the DHCP client would recognize that this message was intended for itself by inclusion of its MAC address in one of the message fields. The networking stack on the client computer can now use the configuration information presented to it by the DHCP server to set up its own network layer configuration. At this stage, The computer that's acting as the DHCP client should have all the information it needs to operate in a full-fledged manner on the network it's connected to. All of this configuration is known as DHCP lease, as it includes an expiration time. A DHCP lease might last for days or only for a short amount of time. Once a lease has expired, the DHCP client would need to negotiate a new lease by performing the entire DHCP discovery process all over again. A client can also release its lease to the DHCP server, which it would do when it disconnects from the network. This would allow the DHCP server to return the IP address that was assigned to its pool of available IPs. Now that you've seen DHCP in action, we've got a short quiz for you. When you're finished, it's time for you to learn the basics of NAT. Welcome back. Ready to dive right in? So, unlike protocols like DNS and DHCP, network address translation, or NAT, is a technique instead of a defined standard. This means that some of what we'll discuss in this lesson might be more high level than some of our other topics. Different operating systems and different network hardware vendors have implemented the details of NAT in different ways, but the concepts of what it accomplishes are pretty constant. Network address translation does pretty much what it sounds like. It takes one IP address and translates it into another. There are lots of reasons why you would want to do this. They range from security safeguards to preserving the limited amounts of available IPv4 space. We'll discuss the implications of NAT and the IPv4 address space later in this lesson. But for now, let's just focus on how NAT itself works and how it can provide additional security measures to a network. At its most basic level, NAT is a technology that allows a gateway, usually a router or firewall, to rewrite the source IP of an outgoing IP datagram while retaining the original IP in order to rewrite it into the response. To explain this better, let's look at a simple NAT example. Let's say we have two networks. Network A consists of the 10.1.1.0/24 address space, and network B consists of the 192.168.1.0/24 address space. Sitting between these networks is a router that has an interface on network A with an IP of 10.1.1.1 and an interface on network B of 192.168.1.1. Now, let's put two computers on these networks. Computer 1 is on network A and has an IP of 10.1.1.100. And computer 2 is on network B and has an IP of 192.168.1.100. Computer 1 wants to communicate with a web server on computer 2. So it crafts the appropriate packet at all layers and sends this to its primary gateway, the router sitting between the two networks. So far, this is a lot like many of our earlier examples, but in this instance, the router is configured to perform NAT for any outbound packets. Normally, a router will inspect the contents of an IP datagram, decrement the TTL by 1, recalculate the checksum, and forward the rest of the data at the network layer without touching it. But with NAT, the router will also rewrite the source IP address, which in this instance becomes the router's IP on network B, or 192.168.1.1. When the datagram gets to computer 2, it'll look like it originated from the router, not from computer 1. Now, computer 2 crafts its response and sends it back to the router. The router, knowing that this traffic is actually intended for computer 1, rewrites the destination IP field before forwarding it along. What NAT is doing in this example is hiding the IP of computer 1 from computer 2. This is known as IP masquerading. IP masquerading is an important security concept. The most basic concept at play here is that no one can establish a connection to your computer if they don't know what IP address it has. By using NAT in the way we've just described, we could actually have hundreds of computers on network A, all of their IPs being translated by the router to its own. To the outside world, the entire address space of network A is protected and invisible. This is known as one-to-many NAT, and you'll see it in use on lots of LANs today. NAT at the network layer is pretty easy to follow. One IP address is translated to another by a device, usually a router. But at the transport layer, things get a little bit more complicated, and several additional techniques come into play to make sure everything works properly. With one-to-many NAT, we've talked about how hundreds, even thousands of computers can all have their outbound traffic translated via NAT to a single IP. This is pretty easy to understand when the traffic is outbound, but a little more complicated once return traffic is involved. We now have potentially hundreds of responses all directed at the same IP, and the router at this IP needs to figure out which responses go to which computer. The simplest way to do this is through port preservation. Port preservation is a technique where the source port chosen by a client is the same port used by the router. Remember that outbound connections choose a source port at random from the ephemeral ports, or the ports in the range 49,152 through 65,535. In the simplest setup, a router set up to NAT outbound traffic will just keep track of what this source port is, and use that to direct traffic back to the right computer. Let's imagine a device with an IP of 10.1.1.100. It wants to establish an outbound connection, and the networking stack of the operating system chooses port 51,300 for this connection. Once this outbound connection gets to the router, it performs network address translation and places its own IP in the source address field of the IP datagram. But it leaves the source port in the TCP datagram the same and stores this data internally in a table. Now, when traffic returns to the router on port 51,300, it knows that this traffic needs to be forwarded back to the IP 10.1.1.100. Even with how large the set of ephemeral ports is, it's still possible for two different computers on a network to both choose the same source port around the same time. When this happens, the router normally selects an unused port at random to use instead. Another important concept about NAT and the transport layer is port forwarding. Port forwarding is a technique where specific destination ports can be configured to always be delivered to specific nodes. This technique allows for complete IP masquerading while still having services that can respond to incoming traffic. Let's use our network 10.1.1.0/24 again to demonstrate this. Let's say there's a web server configured with an IP of 10.1.1.5. With port forwarding, no one would even have to know this IP. Prospective web clients would only have to know about the external IP of the router. Let's say it's 192.168.1.1. Any traffic directed at port 80 on 192.168.1.1 would get automatically forwarded to 10.1.1.5. Response traffic would have the source IP rewritten to look like the external IP of the router. This technique not only allows for IP masquerading, it also simplifies how external users might interact with lots of services all run by the same organization. Let's imagine a company with both a web server and a mail server. Both need to be accessible to the outside world, but they run on different servers with different IPs. Again, let's say the web server has an IP of 10.1.1.5, and the mail server has an IP of 10.1.1.6. With port forwarding, traffic for either of these services could be aimed at the same external IP, and therefore the same DNS name. But it would get delivered to entirely different internal servers due to their different destination ports. The IANA has been in charge of distributing IP addresses since 1988. Since that time, the internet has expanded at an incredible rate. The 4.2 billion possible IPv4 addresses have been predicted to run out for a long time, and they almost have. For For some time now, the IANA has primarily been responsible with assigning address blocks to the 5 regional internet registries, or RIRs. The 5 RIRs are AFNIC, which serves the continent of Africa, ARIN, which serves the United States, Canada, and parts of the Caribbean, APNIC, which is responsible for most of Asia, Australia, New Zealand, and Pacific Island nations, LACNIC, which covers Central and South America and any parts of the Caribbean not covered by ARIN, and finally, RIPE, which serves Europe, Russia, and the Middle East and portions of Central Asia. These 5 RIRs have been responsible for assigning IP address blocks to organizations within their geographic areas, and most have already run out. The IANA assigned the last unallocated /8 network blocks to various RIRs on February 3rd, 2011. Then, in April 2011, APNIC ran out of addresses. RIPE was next, in September of 2012. LACNIC ran out of addresses to assign in June 2014, and ARIN did the same in September 2015. Only AFNIC has some IPs left, but those are predicted to be depleted by 2018. Wikipedia has a great article all about IPv4 exhaustion and the timelines involved. I've added a link to it in the reading just after this video. This is, of course, a major crisis for the internet. IPv6 will eventually resolve these problems, and we'll cover it in more detail later in this course. But implementing IPv6 worldwide is gonna take some time. For now, we want it to continue to grow, and we want more people and devices to connect to it. But without IP addresses to assign, a workaround is needed. Spoiler alert, you already know about the major components of this workaround: NAT and non-routable address space. Remember that non-routable address space was defined in RFC 1918 and consists of several different IP ranges that anyone can use. An unlimited number of networks can use non-routable address space internally because internet routers won't forward traffic to it. This means there's never any global collision of IP addresses when people use those address spaces. Non-routable address space is largely usable today because of technologies like NAT. With NAT, you can have hundreds, even thousands of machines using non-routable address space. Yet, with just a single public IP, all those computers can still send traffic to and receive traffic from the internet. All you need is one single IPv4 address, and via NAT, a router with that IP can represent lots and lots of computers behind it. It's not a perfect solution, but until IPv6 becomes more globally available, non-routable address space and NAT will have to do. Businesses have lots of reasons to want to keep their network secure, and they do this by using some of the technologies we've already discussed. Firewalls, NAT, the use of non-routable address space, things like that. Organizations often have proprietary information that needs to remain secure, network services that are only intended for employees to access, and other things. One of the easiest ways to keep networks secure is to use various securing technologies so only devices physically connected to their local area network can access these resources. But employees aren't always in the office. They might be working from home or on a business trip, and they might still need access to these resources in order to get their work done. That's where VPNs come in. Virtual private networks, or VPNs, are a technology that allows for the extension of a private or local network to hosts that might not work on that same local network. VPNs come in many flavors and accomplish lots of different things. But the most common example of how VPNs are used is for employees to access their business's network when they're not in the office. VPNs are a tunneling protocol, which means they provision access to something not locally available. When establishing a VPN connection, you might also say that a VPN tunnel has been established. Let's go back to the example of an employee who needs to access company resources while not in the office. The employee could use a VPN client to establish a VPN tunnel to their company network. This would provision their computer with what's known as a virtual interface with an IP that matches the address space of the network they've established a VPN connection to. By sending data out of this virtual interface, the computer could access internal resources just like if it was physically connected to the private network. Most VPNs work by using the payload section of the transport layer to carry an encrypted payload that actually contains an entire second set of packets: the network, the transport, and the application layers of a packet intended to traverse the remote network. Basically, this payload is carried to the VPN's endpoint, where all the other layers are stripped away and discarded. Then, the payload is unencrypted, leaving the VPN server with the top 3 layers of a new packet. This gets encapsulated with the proper data link layer information and sent out across the network. This process is completed in the inverse, in the opposite direction. VPNs usually require strict authentication procedures in order to ensure that they can only be connected to by computers and users authorized to do so. In fact, VPNs were one of the first technologies where two-factor authentication became common. Two-factor authentication is a technique where more than just a username and password are required to authenticate. Usually, a short-lived numerical token is generated by the user through a specialized piece of hardware or software. VPNs can also be used to establish site-to-site connectivity. Conceptually, there isn't much difference between how this works compared to our remote employee situation. It's just that the router, or sometimes a specialized VPN device on one network, establishes the VPN tunnel to the router or VPN device on another network. This way, two physically separated offices might be able to act as one network and access network resources across the tunnel. It's important to call out that just like NAT, VPNs are a general technology concept, not a strictly defined protocol. There are lots of unique implementations of VPNs, and the details of how they all work can differ a ton. The most important takeaway is that VPNs are a technology that use encrypted tunnels to allow for a remote computer or network to act as if it's connected to a network that it's not actually physically connected to. A proxy service is a server that acts on behalf of a client in order to access another service. Proxies sit between clients and other servers, providing some additional benefit: anonymity, security, content filtering, increased performance, a couple other things. If any part of this sounds familiar, that's good. We've already covered some specific examples of proxies, like gateway routers. You don't hear them referred to this way, but a gateway definitely meets the definition of what a proxy is and how it works. The concept of a proxy is just that, a concept or an abstraction. It doesn't refer to any specific implementation. Proxies exist at almost every layer of our networking model. There are dozens and dozens of examples of proxies you might run into during your career, but we'll cover just a few of the most common ones here. Most often, you'll hear the term proxy used to refer to web proxies. As you might guess, these are proxies specifically built for web traffic. A web proxy can serve lots of purposes. Many years ago, when most internet connections were much slower than they are today, lots of organizations used web proxies for increased performance. Using a web proxy, an organization would direct all web traffic through it, allowing the proxy server itself to actually retrieve the web page data from the internet. It would then cache this data. This way, if someone else requested the same web page, it could just return the cached data instead of having to retrieve the fresh copy every time. This kind of proxy is pretty old, and you won't often find them in use today. Why? Well, for one thing, most organizations now have connections fast enough that caching individual web pages doesn't provide much benefit. Also, the web has become much more dynamic. Going to www.twitter.com is going to look different to every person with their own Twitter account, so caching this data wouldn't do much good. A more common use of a web proxy today might be to prevent someone from accessing sites like Twitter entirely. A company might decide that accessing Twitter during work hours reduces productivity. By using a web proxy, they can direct all web traffic to it, allow the proxy to inspect what data is being requested, and then allow or deny this request depending on what site is being accessed. Another example of a proxy is a reverse proxy. A reverse proxy is a service that might appear to be a single server to external clients, but actually represents many servers living behind it. A good example of this is how lots of popular websites are architected today. Very popular websites like Twitter receive so much traffic that there's no way a single web server could possibly handle all of it. A website that popular might need many, many web servers in order to keep up with processing all incoming requests. A reverse proxy in this situation could act as a single front end for many web servers living behind it. From the client's perspective, it looks like they're all connected to the same server. But behind the scenes, this reverse proxy server is actually distributing these incoming requests to lots of different physical servers. Much like the concept of DNS round robin, this is a form of load balancing. Another way that reverse proxies are commonly used by popular websites is to deal with decryption. More than half of all traffic on the web is now encrypted, and encrypting and decrypting data is a process that can take a lot of processing power. You'll learn a lot more about encryption and how it works in another course in this program. Reverse proxies are now implemented in order to use hardware built specifically for cryptography to perform the encryption and decryption work so that the web servers are free to just serve content. Proxies come in many other flavors, way too many for us to cover them all here. But the most important takeaway is that proxies are any server that act as an intermediary between a client and another server. Good job. We covered a lot. Take a break for a bit before you move on to the quiz and project we've cooked up for you. Once you're done with these, take another break and then meet me back here for the next module where we'll cover the history of internet connections. The internet is a vast and diverse place. Not only is it huge, the number of different devices connected to it can be just as staggering. And if we were to actually describe all these devices, they'd have an almost endless number of functions. The devices that connect to the internet fall into familiar silos: desktop and laptop computers, servers and data centers, routers and switches that direct network traffic, etc. But this list also includes things like tablets and cell phones, ATMs, industrial equipment, medical devices, and even some cars are now connected to the internet. The list could go on and on. It's nice and simple to discuss everything in terms of a basic physical layer made up of Cat5 or Cat6 cables, and a data link layer made entirely of Ethernet. But that's not exactly how things work when they actually connect to the internet. The technologies used to get people and devices connected are as different as the people and devices themselves. By the end of this module, you'll be able to describe various internet connectivity technologies. You'll also be able to define the components of WANs and outline the basics of wireless and cellular networking. These are the skills important as an IT support specialist because a big part of your job will be making sure people can get online. See you at the top of the next video. As computer use grew over the course of the 20th century, it became obvious that there was a big need to connect computers to each other so that they could share data. For years before Ethernet, TCP, or IP were ever invented, there were computer networks made up of technologies way more primitive than the model we've been discussing. These early networking technologies mostly focused on connecting devices within close physical proximity to each other. In the late 1970s, two graduate students at Duke University were trying to come up with a better way to connect computers at further distances. They wanted to share what was essentially bulletin board material. Then a light bulb moment went off. They realized the basic infrastructure for this already existed: the public telephone network. The public switched telephone network, or PSTN, is also sometimes referred to as the plain old telephone service, or POTS. It was already a pretty global and powerful system by the late 1970s, more than 100 years after the invention of the telephone. These Duke grad students weren't the first ones to think about using a phone line to transmit data, but they were the first to do it in a way that became somewhat permanent precursor to the dial-up networks to follow. The system they built is known as Usenet, and a form of it is still in use today. At the time, different locations like colleges and universities used a very primitive form of a dial-up connection to exchange a series of messages with each other. A dial-up connection uses POTS for data transfer and gets its name because the connection is established by actually dialing a phone number. If you used dial-up back in the day, this noise might sound familiar to you. For some of us, it was like nails on a chalkboard as we waited to get connected to the internet. Transferring data across a dial-up connection is done through devices called modems. Modem stands for modulator demodulator, and they take data that computers can understand and turn them into audible wavelengths that can be transmitted over POTS. After all, the telephone system was developed to transmit voice messages or sounds from one place to another. This is conceptually similar to how line coding is used to turn ones and zeros into modulating electrical charges across Ethernet cables. Early modems had very low baud rates. A baud rate is a measurement of how many bits could be passed across a phone line in a second. By the late 1950s, computers could generally only send each other data across a phone line at about 110 bits per second. By the time Usenet was being developed, this rate had increased to around 300 bits per second. And by the time dial-up access to the internet became a household commodity in the early 1990s, this rate had increased to 14.4 kilobits per second. Improvements continue to be made, but widespread adoption of broadband technologies, which we'll discuss in the next lesson, replaced a lot of these improvements. Dial-up internet connectivity is pretty rare today, but it hasn't completely gone away. In some rural areas, it might be the only option still available. You might never run into a dial-up internet connection during your IT career, but it's still important to know that for several decades, this technology represented the main way computers communicated with each other over long distances. I'm just glad we don't have to choose between using the phone or using the internet anymore. Next, let's take a deep dive into the world of broadband. The term broadband has a few definitions. In terms of internet connectivity, it's used to refer to any connectivity technology that isn't dial-up internet. Broadband internet is almost always much faster than even the fastest dial-up connections and refers to connections that are always on. This means that they're long-lasting connections that don't need to be established with each use. They're essentially links that are always present. Broadband shaped today's world. While the internet itself is a totally amazing invention, it wasn't until the advent of broadband technologies that its true potential for business and home users was realized. Long before people had broadband connections at home, businesses spent a lot of resources on them, usually out of necessity. If you had an office with more than a few employees, the bandwidth available by a single dial-up connection would quickly be oversaturated by just a few users. By the mid-1990s, it had become pretty common for businesses that needed internet access for their employees to use various T-carrier technologies. T-carrier technologies were originally invented by AT&T in order to transmit multiple phone calls over a single link. Eventually, they also became common transmission systems to transfer data much faster than any dial-up connection could handle. We'll cover the details of T-carrier technologies in an upcoming lesson. After businesses got into the broadband game, home use became more prevalent. As different aspects of the internet, like the World Wide Web, became more complex, they also required ever-increasing data transfer rates. In the days of dial-up, even a single image on a web page could take many seconds to download and display. high-resolution photos that you can now take on a cell phone would have required a long time to download and a lot of your patience. A single picture taken on a smartphone today can easily be several megabytes in size. 2 megabytes would translate to 16,777,216 bits. At a baud rate of 14.4 kilobits per second, that many bits would take nearly 20 minutes to download. No one would have had time to download all the hilarious cat images on the internet back then. What a travesty! Without broadband internet connection technologies, the internet as we know it today wouldn't exist. We wouldn't be able to stream music or movies or easily share photos. You definitely couldn't be taking an online course like this. T-carrier technologies require dedicated lines, which makes them more expensive. For this reason, you usually only see them in use by businesses. But other broadband solutions also exist for both businesses and consumers. In the next few videos, we'll deep dive into 4 of the most common broadband solutions available today: T-carrier technologies, digital subscriber lines or DSL, cable broadband, and fiber connections. Are you ready? Let's get started. T-carrier technologies were first invented by AT&T in order to provision a system that allowed lots of phone calls to travel across a single cable. Every individual phone call was made over individual pairs of copper wire before Transmission System 1, the first T-carrier specification, called T1 for short. With the T1 specification, AT&T invented a way to carry up to 24 simultaneous phone calls across a single piece of twisted pair copper. Years later, this same technology was repurposed for data transfers. Each of the 24 phone channels was capable of transmitting data at 64 kilobits per second, making a single T1 line capable of transmitting data at 1.544 megabits per second. Over the years, the phrase T1 has come to mean any twisted pair copper connection capable of speeds of 1.544 megabits per second, even if it doesn't strictly follow the original Transmission System 1 specification. Originally, T1 technology was only used to connect different telecom company sites to each other and to connect these companies to other telecom companies. But with the rise of the internet as a useful business tool, in the 1990s, more and more businesses started to pay to have T1 lines installed at their offices to have faster internet connectivity. More improvements to the T1 line were made by developing a way of multiple T1s to act as a single link. So a T3 line is 28 T1s all multiplexed, achieving a total throughput speed of 44.736 megabits per second. You'll still find T-carrier technologies in use today, but they've usually been surpassed by other broadband technologies. For small business offices, cable broadband or fiber connections are now way more common since they're much cheaper to operate. For inter-ISP communications, different fiber technologies have all replaced older copper-based ones. The public telephone network was a great option for getting people connected to the internet since it already had infrastructure everywhere. For a long time, dial-up connections were the main way that people connected to the internet from home. But there were certain limitations with trying to transmit data as what were essentially just audio waves. As people wanted faster and faster internet access, telephone companies began to wonder if they could use the same infrastructure but in a different way. The research showed that twisted pair copper used by modern telephone lines was capable of transmitting way more data than what was needed for voice-to-voice calls. By operating at a frequency range that didn't interfere with normal phone calls, a technology known as digital subscriber line, or DSL, was able to send much more data across the wire than traditional dial-up technologies. And to top it all off, this allowed for normal voice phone calls and data transfer to occur at the same time on the same line. Kind of like how dial-up uses modems, DSL technologies also use their own modems. But more accurately, they're known as DSLAMs, or Digital Subscriber Line Access Multiplexers. Just like dial-up modems, These devices establish data connections across phone lines, but unlike dial-up connections, they're usually long-running. This means that the connection is generally established when the DSLAM is powered on and isn't torn down until the DSLAM is powered off. There are lots of different kinds of DSL available, but they all vary in a pretty minor way. For a long time, the two most common types of DSL were ADSL and SDSL. ADSL stands for Asymmetric Digital Subscriber Line. ADSL connections feature different speeds for outbound and incoming data. Generally, this means faster download speeds and slower upload speeds. Home users rarely need to upload as much data as they download, since home users are mostly just clients. For example, when you open a web page in a web browser, the upload or outbound data is pretty small. You're just asking for a certain web page from the web server. The download or inbound data tends to be much larger, since it'll contain the entire web page, including all images and other media. For this reason, asymmetric lines often provide a similar user experience for a typical home user, but at a lower cost. SDSL, as you might be able to guess, stands for Symmetric Digital Subscriber Line. SDSL technology is basically the same as ADSL, except the upload and download speeds are the same. At one point, SDSL was mainly used by businesses that hosted servers that needed to send data to clients. As the general bandwidth available on the internet has expanded, and as the cost of operation have come down over the years, SDSL is now more common for both businesses and home users. Most SDSL technologies have an upper cap of 1.544 megabits a second, or the same as a T1 line. Further developments in SDSL technology have yielded things like HDSL, or high bitrate digital subscriber lines. These are DSL technologies that provision speeds above 1.544 megabits per second. There are lots of other minor variations in DSL technology out in the wild, offering different bandwidth options and operating distances. These variations can be so numerous and minor, it's not really practical to try to cover them here. If you ever need to know more about a specific DSL line, you should contact the ISP that provides it for more details. The history of both the telephone and computer networking tells a story that started with all communications being wired. But the recent trend is moving towards more and more of this traffic becoming wireless. The history of television follows the opposite path. Originally, all television broadcasts were wireless transmissions, sent out by giant television towers and received by smaller antennas in people's homes. This meant you had to be within range of one of these television towers to watch TV, just like you have to be within range of a cell phone tower to use your cell phone today. Starting in the late 1940s in the United States, the first cable television technologies were developed. At the time, they mainly wanted to provide television access to remote towns and rural homes that were out of range of capabilities of television towers at the time. Cable television continued to expand slowly over the decades, but in 1984, the Cable Communications Policy Act was passed. This deregulated the cable television business in the United States and caused a massive boom in growth and adoption. Other countries all over the globe soon followed. By the early 1990s, cable television infrastructure in the United States was about the size of the public telephone system. Not too long after that, cable providers started trying to figure out if they could join in on the massive spike in internet growth that was happening at the same time. Much like how DSL was developed, cable companies quickly realized that the coaxial cables generally used by cable television delivery into a person's home were capable of transmitting much more data than what was required for TV viewing. By using frequencies that don't interfere with television broadcasts, cable-based internet access technologies were able to deliver high-speed internet access across these same cables. This is the technology we refer to when we say cable broadband. One of the main differences in how cable internet access works when compared to other broadband solutions is that cable is generally what's known as a shared bandwidth technology. With technologies like DSL or even dial-up, The connection from your home or business goes directly to what's known as a central office, or CO. A long time ago, these COs were actually offices staffed with telephone operators who used a switchboard to manually connect the caller with the callee. As technology improved, these COs became smaller pieces of automated hardware that handled these functions for the telephone companies, but the name stayed the same. Technologies that connect directly to a CO can guarantee a certain amount of bandwidth available over that connection since it's point-to-point. On the flip side of this are cable internet technologies, which employ a shared bandwidth model. With this model in place, many users share a certain amount of bandwidth until the transmissions reach the ISP's core network. This could be anywhere from a single city block to entire subdivisions in the suburbs. It just depends on how that area was originally wired for cable. Today, most cable operators have tried to upgrade their networks to the point that end users might not always notice this shared bandwidth. But it's also still common to see cable internet connections slow down during periods of heavy use, like when lots of people in the same region are using their internet connection at the same time. Cable internet connections are usually managed by what's known as a cable modem. This is a device that sits at the edge of a consumer's network and connects it to the cable modem termination system, or CMTS. The CMTS is what connects lots of different cable connections to an ISP's core network. The core of the internet has long used fiber for its connections, both due to higher speeds and because fiber allows for transmission to travel much further without degradation of the signal. Remember that fiber connections use light for data transmission instead of electrical currents. The absolute maximum distance an electrical signal can travel across a copper cable before it degrades too much and requires a repeater is thousands of feet. But certain implementations of fiber connections can travel many, many miles before signal degrades. Producing and laying fiber is a lot more expensive than using copper cables. So for a long time, it was a technology you only saw in use by ISPs within their core networks, or maybe for use within data centers. But in recent years, it's become popular to use fiber to deliver data closer and closer to the end user. Exactly how close to the end user can vary a ton across implementations, which is why the phrase FTTX was developed. FTTX stands for fiber to the X, where the X can be one of many things. We'll cover a few of these possibilities. The first term you might hear is FTTN, which means fiber to the neighborhood. This means that fiber technologies are used to deliver data to a single physical cabinet that serves a certain amount of the population. From this cabinet, twisted pair copper or coax might be used for the last length of distance. The next version you might come across is FTTB. This stands for fiber to the building, fiber to the business, or even fiber to the basement, since this is generally where cables to buildings physically enter. FTTB is a setup where fiber technologies are used for data delivery to an individual building. After that, twisted pair copper is typically used to actually connect those inside of the building. A third version you might hear is FTTH, which stands for fiber to the home. This is used in instances where fiber is actually run to each individual residence in a neighborhood or apartment building. FTTH and FTTB may both also be referred to as FTTP, fiber to the premises. Instead of a modem, the demarcation point for fiber technologies is known as optical network terminator, or ONT. An ONT converts data from protocols the fiber network can understand to those that more traditional twisted pair copper networks can understand. Let's say that you're in charge of the network as the sole IT support specialist at a small company. At first, the business only has a few employees with a few computers in a single office. You decide to use non-routable address space for the internal IPs because IP addresses are scarce and expensive. You set up a router and configure it to perform NAT. You configure a local DNS server and a DHCP server to make network configuration easier. And of course, for all of this to really work, you sign a contract with an ISP to deliver a link to the internet to this office, so your users can access the web. Now imagine the company grows. You're using non-routable address space for your internal IPs, so you have plenty of space to grow there. Maybe some salespeople need to connect to resources on the LAN you've set up while they're on the road. So you configure a VPN server and make sure the VPN server is accessible via port forwarding. Now, you can have employees from all over the world connect to the office LAN. Business is good and the company keeps growing. The CEO decides that it's time to open a new office in another city across the country. Suddenly, instead of a handful of salespeople requiring remote access to the resources on your network, you have an entire second office that needs it. This is where wide area networks, or WAN technologies, come into play. Unlike a LAN or a local area network, WAN stands for wide area network. A wide area network acts like a single network, but spans across multiple physical locations. WAN technologies usually require that you contract a link across the internet with your ISP. This ISP handles sending your data from one site to the other. So it could be like all of your computers are in the same physical location. A typical WAN setup has a few sections. Imagine one network of computers on one side of the country and another network of computers on the other. Each of those networks ends at a demarcation point, which is where the ISP's network takes over. The area between each demarcation point and the ISP's actual core network is called a local loop. This local loop would be something like a T-carrier line or a high-speed optical connection to the provider's local regional office. From there, it would connect out to the ISP's core network and the internet at large. WANs work by using a number of different protocols at the data link layer to transport your data from one site to another. In fact, these same protocols are what are sometimes at work at the core of the internet itself, instead of our more familiar Ethernet. Covering all the details of these protocols is out of the scope of this course, but in an upcoming lesson, we'll give you some links to the most popular WAN protocols. A popular alternative to WAN technologies are point-to-point VPNs. WAN technologies are great for when you need to transport large amounts of data across lots of sites, because WAN technologies are built to be super fast. A business cable or a DSL line might be way cheaper, but it just can't handle the load required in some of these situations. But over the last few years, companies have been moving more and more of their internal services into the cloud. We'll cover exactly what this means later, but for now, it's enough to know that the cloud lets companies outsource all or part of their different pieces of infrastructure to other companies to manage. Let's take the concept of email. In the past, a company would have to run their own email server if they wanted an email presence at all. Today, you could just have a cloud hosting provider host your email server for you. You could even go a step further and use an email as a service provider. Then you wouldn't have an email server at all anymore. You just have to pay another company to handle everything about your email service. With these types of cloud solutions in place, lots of businesses no longer require extreme high-speed connections between their sites. This makes the expense of a WAN technology totally unnecessary. Instead, companies can use point-to-point VPNs to make sure that their different sites can still communicate with each other. A point-to-point VPN, also called a site-to-site VPN, establishes a VPN tunnel between two sites. This operates a lot like the way that a traditional VPN setup lets individual users act as if they're on the network they're connecting to. It's just that the VPN tunneling logic is handled by network devices at either side, so that users don't all have to establish their own connections. Now, it's time for one more quiz to see how your connections are firing. In today's world, fewer and fewer devices are weighed down by physical cables in order to connect to computer networks. With so many portable computing devices in use, from laptops to tablets to smartphones, we've also seen the rise of wireless networking. Wireless networking is exactly what it sounds like, a way to network without wires. By the end of this lesson, you'll be able to describe the basics of how wireless communication works. You'll know how to tell the difference between infrastructure networks and ad hoc networks. You'll be able to explain how wireless channels help wireless networks operate, and you'll understand the basics of wireless security protocols. These are all invaluable skills as an IT support specialist, since wireless networks are becoming more and more common in the workplace. The most common specifications for how wireless networking devices should communicate are defined by the IEEE 802.11 standards. This set of specifications, also called the 802.11 family, make up the set of technologies we call Wi-Fi. Wireless networking devices communicate with each other through radio waves. Different 802.11 standards generally use the same basic protocol, but might operate at different frequency bands. A frequency band is a certain section of the radio spectrum that's been agreed upon to be used for certain communications. In North America, FM radio transmissions operate between 88 and 108 megahertz. This specific frequency band is called the FM broadcast band. Wi-Fi networks operate on a few different frequency bands, most commonly the 2.4 gigahertz and 5 gigahertz bands. There are lots of 802.11 specifications, including some that exist just experimentally or for testing. The most common specifications you might run into are 802.11b, 802.11a, 802.11g, 802.11n, and 802.11ac. We won't go into detail about each one here. For now, just know that we've listed these in the order they were adopted. Each newer version of the 802.11 specifications has generally seen some improvement, whether it's higher access speeds or the ability for more devices to use the network simultaneously. In terms of our networking model, you should think of 802.11 protocols as defining how we operate at both the physical and the data link layers. An 802.11 frame has a number of fields. The first is called the frame control field. This field is 16 bits long and contains a number of subfields that are used to describe how the frame itself should be processed. This includes things like what version of the 802.11 was used. The next field is called a duration field. It specifies how long the total frame is, so the receiver knows how long it should expect to have to listen to the transmission. After this are 4 address fields. Let's take a moment to talk about why there are 4, instead of the normal 2. We'll discuss different types of wireless network architectures in more detail later in this lesson, but the most common setup includes devices called access points. A wireless access point is a device that bridges the wireless and wired portions of a network. A single wireless network might have lots of different access points to cover a large area. Devices on a wireless network will associate with a certain access point. This is usually the one they're physically closest to, but it can also be determined by all sorts of other things, like general signal strength and wireless interference. Associations isn't just important for the wireless device to talk to a specific access point. It also allows for incoming transmissions to the wireless device to be sent by the right access point. There are 4 address fields, because there needs to be room to indicate which wireless access point should be processing the frame. So we'd have our normal source address field, which would represent the MAC address of the sending device, but we'd also have the intended destination on the network, along with a receiving address and a transmitter address. The receiver address would be the MAC address of the access point that should receive the frame, and the transmitter address would be the MAC address of whatever has just transmitted the frame. In lots of situations, the destination and receiver address might be the same. Usually, the source and transmitter addresses are also the same. But depending on exactly how a specific wireless network has been architected, this won't always be the case. Sometimes, wireless access points will relay these frames from one another. Since all addresses in an 802.11 frame are MAC addresses, each of those 4 fields is 6 bytes long. In between the 3rd and 4th address fields, you'll find the sequence control field. The sequence control field is 16 bits long and mainly contains a sequence number used to keep track of ordering the frames. After this is the data payload section, which has all of the data of the protocols further up the stack. Finally, we have a frame check sequence field, which contains a checksum used for a cyclical redundancy check, just like how Ethernet does it. There are a few main ways that a wireless network can be configured. There are ad hoc networks, where nodes all speak directly to each other. There are wireless LANs or WLANs, where one or more access points act as a bridge between a wireless and a wired network. And there are mesh networks, which are kind of a hybrid of the two. Ad hoc networks are the simplest of the three. In an ad hoc network, there isn't really any supporting network infrastructure. Every device involved with the network communicates with every other device within range, and all nodes help pass along messages. Even though they're the most simple, ad hoc networks aren't the most common type of wireless network, but they do have some practical applications. Some smartphones can establish ad hoc networks with other smartphones in the area so that people can exchange photos, video, or contact information. You'll also sometimes see ad hoc networks used in industrial or warehouse settings, where individual pieces of equipment might need to communicate with each other, but not with anything else. Finally, ad hoc networks can be powerful tools during disaster situations. If a natural disaster like an earthquake or hurricane knocks out all of the existing infrastructure in an area, disaster relief professionals can use an ad hoc network to communicate with each other while they perform search and rescue efforts. The most common type of wireless network you'll run into in the business world is a wireless LAN, or WLAN. A wireless LAN consists of one or more access points which act as bridges between the wireless and wired networks. The wired network operates as a normal LAN, like the types we've already discussed. The wired LAN contains the outbound internet link. In order to access resources outside of the WLAN, wireless devices would communicate with access points. They then forward traffic along to the gateway router where everything proceeds like normal. Finally, we have what's known as mesh networks. Mesh networks are kind of like ad hoc networks since lots of the devices communicate with each other wirelessly, forming a mesh if you were to draw lines for all the links between all the nodes. Most mesh networks you'll run into are made up of only wireless access points and will still be connected to a wired network. This kind of network lets you deploy more access points to the mesh without having to run a cable to each of them. With this kind of setup, you can really increase the performance and range of a wireless network. The concept of channels is one of the most important things to understand about wireless networking. Channels are individual, smaller sections of the overall frequency band used by a wireless network. Channels are super important because they help address a very old networking concern: collision domains. You might remember that a collision domain is any one network segment where one computer can interrupt another. Communications that overlap each other can't be properly understood by the receiving end. So when two or more transmissions occur at the same time, also called a collision, all devices in question have to stop their transmissions. They wait a random amount of time and try again when things quiet down. This really slows things down. The problem caused by collision domains has been mostly reduced on wired networks through devices called switches. Switches remember which computers live on which physical interfaces, so traffic is only sent to the node it's intended for. Wireless networking doesn't have cables, so there aren't physical interfaces for a wireless device to connect to. That means we can't have something that works like a wireless switch. Wireless devices are doomed to talk over each other. Channels help fix this problem to a certain extent. When we were talking about the concept of frequency bands, we mentioned that FM radio in North America operates between 88 MHz and 108 MHz. But when we discuss the frequency bands we use by Wi-Fi, we just mentioned 2.4 GHz and 5 GHz. This is because that's really just shorthand for where these frequency bands actually begin. For wireless networks that operate on the 2.4 GHz band, what we really mean is that they operate on roughly the band from 2.4 GHz to 2.5 GHz. Between these two frequencies are a number of channels, each with a width of a certain megahertz. Since different countries and regions have different regulatory committees for what radio frequencies might be used for what, exactly how many channels are available for use depends on where in the world you are. For example, dealing with an 802.11b network, channel 1 operates at 2412 MHz, but since the channel width is 22 MHz, the signal really lives on the frequencies between 2401 MHz and 2423 MHz. This is because radio waves are imprecise things, so you need some buffer around what exact frequencies a transmission might actually arrive on. Some channels overlap, but some are far enough apart so they won't interfere with each other at all. Let's look again at an 802.11b network running on the 2.4 GHz band, because it's really the simplest and the concepts translate to all other 802.11 specifications. With a channel width of 22 MHz, channel 1, with its midpoint at 2412 MHz, is always completely isolated from channel 6, with its midpoint at 2437 MHz. For an 802.11b network, this means that channels 1 and 6 and 11 are the only ones that never overlap at all. That's not all that matters though. Today, most wireless networking equipment is built to auto-sense what channels are most congested. Some access points will only perform this analysis when they start up. Others will dynamically change their channel as needed. Between those two scenarios and manually specified channels, you can still run into situations where you experience heavy channel congestion. This is especially true in dense urban areas with lots of wireless networks in close proximity. So why is this important in the world of IT support? Well, understanding how these channels overlap for all of the 802.11 specifications is a way you can help troubleshoot bad wireless connectivity problems or slowdowns in the network. You want to avoid collision domains wherever you can. I should call out that it's not important to memorize all of the individual numbers we've talked about. The point is to understand how collision domains are a necessary problem with all wireless networks, and how you can use your knowledge in this space to optimize wireless network deployments. You want to make sure that both your own access points and those of neighboring businesses overlap channels as little as possible. When you're sending data over a wired link, your communication has a certain amount of inherent privacy. The only devices that really know what data is being transmitted are the two nodes on either end of the link. Someone or some device that happens to be in close proximity can't just read the data. With wireless networking, this isn't really the case, since there aren't cables, just radio transmissions being broadcast through the air. Anyone within range could hypothetically intercept any transmissions, whether they were intended for them or not. To solve this problem, WEP was invented. WEP stands for Wired Equivalent Privacy, and it's an encryption technology that provides a very low level of privacy. Actually, it's really right there in the name, Wired Equivalent Privacy. Using WEP protects your data a little, but it should really only be seen as being as safe as sending unencrypted data over a wired connection. The WEP standard is a really weak encryption algorithm. It doesn't take very long for a bad actor to be able to break through this encryption and read your data. You'll learn more about key lengths and encryption in a future course, but for now, it's important to know that the number of bits in an encryption key corresponds to how secure it is. The more bits in a key, the longer it takes for someone to crack the encryption. WEP only uses 40 bits for its encryption keys, and with the speed of modern computers, This can usually be cracked in just a few minutes. WEP was quickly replaced in most places with WPA, or Wi-Fi Protected Access. WPA, by default, uses a 128-bit key, making it a whole lot more difficult to crack than WEP. Today, the most commonly used encryption algorithm for wireless networks is WPA2, an update to the original WPA. WPA2 uses a 256-bit key, making it even harder to crack. Another common way to help secure wireless networks is through MAC filtering. With MAC filtering, you configure your access points to only allow for connections from a specific set of MAC addresses belonging to devices you trust. This doesn't do anything more to help encrypt wireless traffic being sent through the air, but it does provide an additional barrier preventing unauthorized devices from connecting to the wireless network itself. Another super popular form of wireless networking is cellular networking, also called mobile networking. Cellular networks are now common all over the world. In some places, using a cellular network for internet access is the most common way of connecting. At a high level, cellular networks have a lot in common with the 802.11 networks we've already talked about. Just like there are many different 802.11 specifications, there are lots of different cellular specifications. Just like Wi-Fi, cellular networking operates over radio waves, and there are specific frequency bands specifically reserved for cellular transmissions. One of the biggest differences is that these frequencies can travel over longer distances more easily, usually over many kilometers or miles. Cellular networks are built around the concept of cells. Each cell is assigned a specific frequency band for use. Neighboring cells are set up to use bands that don't overlap, just like how we discussed the optimal setup for a WLAN with multiple access points. In fact, the cell towers that broadcast and receive cellular transmissions can be thought of like access points, just with a much larger range. Lots of devices today use cellular networks for communication. And not just phones, also tablets and some laptops also have cellular antennas. It's become more and more common for high-end automobiles to have built-in cellular access too. One module down, one final module to go. Once you're done with the assessments we got for you, I'll see you there. Welcome back. As you've seen, computer networking can be an incredibly complicated business. There are so many layers, protocols, and devices at play, and sometimes this means that things just don't work properly. No surprise there. Many of the protocols and devices we've covered have built-in functionalities to help protect against some of these issues. These functionalities are known as error detection and error recovery. Error detection is the ability for a protocol or program to determine that something went wrong. Error recovery is the ability for a protocol or program to attempt to fix it. For example, you might remember that cyclical redundancy checks are used by multiple layers to make sure that the correct data was received by the receiving end. If a CRC value doesn't match the data payload, the data is discarded. At that point, the transport layer will decide if the data needs to be resent. But even with all of these safeguards in place, errors still pop up. Misconfigurations occur, hardware breaks down, and system incompatibilities come to light. In this module, you'll learn about the most common techniques and tools you use as an IT support specialist when troubleshooting network issues. By the end of this module, you'll be able to detect and fix a lot of the common network connectivity problems by using tools available on the three most common operating systems: Microsoft Windows, Mac OS, and Linux. And finally, at the end of this module, we'll cover some concepts that are super important to the future of networking: the cloud and IPv6. When network problems come up, the most common issue you'll run into is the inability to establish a connection to something. It could be a server you can't reach at all, or a website that isn't loading. Maybe you can only reach your resource on your LAN and can't connect to anything on the internet. Whatever the problem is, being able to diagnose connectivity issues is an important part of network troubleshooting. By the end of this lesson, you'll be able to use a number of important troubleshooting tools to help resolve these issues. When a network error occurs, the device that detects it needs some way to communicate this to the source of the problematic traffic. It could be that a router doesn't know how to route to a destination, or that a certain port isn't reachable. It could even be that the TTL of an IP datagram expired and no further router hops will be attempted. For all of these situations and more, ICMP, or Internet Control Message Protocol, is used to communicate these issues. ICMP is mainly used by a router or remote host to communicate why a transmission has failed back to the origin of the transmission. The makeup of an ICMP packet is pretty simple. It has a header with a few fields and a data section that's used by a host to figure out which of their transmissions generated the error. The first field is the type field, 8 bits long, which specifies what type of message is being delivered. Some examples are destination unreachable or time exceeded. Immediately after this is the code field, which indicates a more specific reason for the message than just the type. For example, of the destination unreachable type, there are individual codes for things like destination network unreachable and destination port unreachable. After this is a 16-bit checksum that works like every other checksum field we've covered so far. Next up is a 32-bit field with an uninspired name, rest of header. You'd think they could come up with something a bit more interesting, but I can't really think of anything good, so who am I to judge? Anyway, this field is optionally used by some of the specific types and codes to send more data. After this is the data payload for an ICMP packet. The payload for an ICMP packet exists entirely so that the recipient of the message knows which of their transmissions caused the error being reported. It contains the entire IP header and the first 8 bytes of the data payload section of the offending packet. ICMP wasn't really developed for humans to interact with. The point is so that these sorts of error messages can be delivered between networked computers automatically. But there's also a specific tool and 2 message types that are very useful to human operators. This tool is called ping. Some version of it exists on just about every operating system and has for a very long time. Ping is a super simple program, and the basics are the same no matter which operating system you're using. Ping lets you send a special type of ICMP message called an echo request. An ICMP echo request essentially just asks a destination, "Hey, are you there?" If the destination is up and running and able to communicate on the network, it'll send back an ICMP echo reply message type. You can invoke the ping command from the command line of any modern operating system. In its most basic use, you just type ping and a destination IP or a fully qualified domain name. If you don't know how to use a command line in an operating system, don't worry, you will soon. We'll cover that in another course. Output of the ping command is very similar across each of the different operating systems. Every line of output will generally display the address sending the ICMP echo reply and how long it took for the round-trip communications. It will also have the TTL remaining and how large the ICMP message is in bytes. Once the command ends, there will also be some statistics displayed, like percentage of packets transmitted and received, the average round-trip time, and a couple other things like that. On Linux and macOS, the ping command will run until it's interrupted by an end user sending an interrupt event. They do this by pressing the Control key and the C key at the same time. On Windows, ping defaults to only sending 4 echo requests. In all environments, ping supports a number of command line flags that let you change its behavior, like the number of echo requests to send, how large they should be, and how quickly they should be sent. Check out the documentation for your operating system to learn a little bit more. With ping, you now have a way to determine if you can reach a certain computer from another one. You can also understand the general quality of the connection. But communications across networks, especially across the internet, usually cross lots of intermediary nodes. Sometimes you need a way to determine where in the long chain of router hops the problems actually are. Traceroute to the rescue. Traceroute is an awesome utility that lets you discover the paths between two nodes and gives you information about each hop along the way. The way Traceroute works is through a clever manipulation technique of the TTL field at the IP level. We learned earlier that the TTL field is decremented by 1 by every router that forwards the packet. When the TTL field reaches 0, the packet is discarded and an ICMP time exceeded message is sent back to the originating host. Traceroute uses the TTL field by first setting it to 1 for the first packet, then 2 for the second, 3 for the third, and so on. By doing this clever little action, Traceroute makes sure that the very first packet sent will be discarded by the first router hop. This results in an ICMP time exceeded message. The second packet will make it to the second router, the third will make it to the third, and so on. This continues until the packet finally makes it all the way to its destination. For each hop, Traceroute will send 3 identical packets. Just like with ping, the output of a traceroute command is pretty simple. On each line, you'll see the number of the hop and the round-trip time for all 3 packets. You'll also see the IP of the device at each hop and a host name if Traceroute can resolve one. On Linux and macOS, Traceroute sends UDP packets to very high port numbers. On Windows, the command has a shortened name, traceRT, and defaults to using ICMP echo requests. On all platforms, Traceroute has more options than can be specified using command line flags. 2 more tools that are similar to Traceroute are MTR on Linux and macOS and PathPing on Windows. These 2 tools act as long-running traceroutes, so you can better see how things change over a period of time. MTR works in real time and will continually update its output with all the current aggregate data about the traceroute. You can compare this with PathPing, which runs for 50 seconds and then displays the final aggregate data all at once. We've covered a bunch of ways to test connectivity between machines at the network layer, but sometimes you need to know if things are working at the transport layer. For this, there are 2 super powerful tools at your disposal: Netcat on Linux and macOS, and Test Net Connection on Windows. The Netcat tool can be run through the command nc and has 2 mandatory arguments, a host and a port. Running nc google.com/80 would try to establish a connection on port 80 to google.com. If the connection fails, the command will exit. If it succeeds, you'll see a blinking cursor waiting for more input. This is a way for you to actually send application layer data to the listening service from your own keyboard. If you're really only curious about the status of a port, you can issue the command with the -z flag, which stands for zero input output mode. The -v flag, which stands for verbose, is also useful in this scenario. This makes the command's output useful to human eyes as opposed to non-verbose output, which is best for usage in scripts. Side note, verbose basically means talking too much. So while I bet you want to throw up a flag on me and my jabbering, we still have lots to get through. Okay, so by issuing the netcat command with the -z and -v flags, the command's output will simply tell you if a connection to the port in question is possible or not. On Windows, Test Net Connection is a command with some of the similar functionality. If you run Test Net Connection with only a host specified, it will default to using an ICMP echo request, much like the program ping. But it will display way more data, including the data link layer protocol being used. When you issue Test Net Connection with the -port flag, you can ask it to test connectivity to a specific port. It's important to call out that both netcat and test net connection are way more powerful than the brief port connectivity examples we've covered here. In fact, they're such complex tools that covering all of their functionality would be too much for one video. You should read up about all of the other things these super powerful tools can do. We provided a few in the supplementary readings, and after you've had a chance to read through the material, we'll give you a short quiz. Name resolution is an important part of how the internet works. Most of the time, your operating system handles all lookups for you. But as an IT support specialist, sometimes it can be useful to run these queries yourself so you can see exactly what's happening behind the scenes. Luckily, there are lots of different command line tools out there to help you with this. The most common tool is known as NSLOOKUP, and it's available on all three of the operating systems we've been discussing, Linux, Mac, and Windows. A basic use of NSLOOKUP is pretty simple. You execute the NSLOOKUP command with the host name following it, and the output displays what server was used to perform the request and the resolution result. Let's say you needed to know the IP address for twitter.com. You would just enter NSLOOKUP twitter.com, and the A record would be returned. NSLOOKUP is way more powerful than just that. It includes an interactive mode that lets you set additional options and run lots of queries in a row. To start an interactive NSLOOKUP session, you just enter NSLOOKUP without any host name following it. You should see an angle bracket acting as your prompt. From interactive mode, you can make lots of requests in a row. You can also perform some extra configuration to help with more in-depth troubleshooting. While in interactive mode, if you type server, then an address, all the following name resolution queries will be attempted to be made using that server instead of the default name server. You can also enter set type equals, followed by a resource record type. By default, NSLOOKUP will return A records, but this lets you explicitly ask for quad A or MX or even text records associated with the host. If you really want to see exactly what's going on, you can enter set debug. This will allow the tool to display the full response packets, including any intermediary requests and all of their contents. Warning, this is a lot of data and can contain details like the TTL left if it's a cached response, all the way to the serial number of the zone file the request was made against. Having functional DNS is an important part of a functional network. An ISP almost always gives you access to a recursive name server as part of the service it provides. In most cases, these name servers are all you really need for your computer to communicate with other devices on the internet. But most businesses also run their own DNS servers. In the very least, this is needed to resolve names of internal hosts. Anything from naming a computer NIAS-laptop to being able to refer to a printer by a name instead of an IP requires your own name server. A third option is to use a DNS as a service provider, and it's getting more and more popular. Don't worry, we'll cover that concept more in an upcoming lesson. No matter what DNS service model you're using on your network, it's useful to have a way to test DNS functionality in case you suspect something isn't working right. It can also be super useful to have a backup DNS option in case you experience problems with your own. You might even be in the early stages of building out a new network, and even if you plan to have your own name server eventually, it may not be ready for use. Some internet organizations run what are called public DNS servers, which are name servers specifically set up so that anyone can use them for free. Using these public DNS servers is a handy technique for troubleshooting any kind of name resolution problems you might be experiencing. Some people just use these name servers for all their resolution needs. For a long time, public DNS servers were a kind of tribal knowledge passed down from one sysadmin to another. In ancient sysadmin lore, it's said that for many years, the most commonly used public DNS servers were those run by Level 3 Communications, one of the largest ISPs in the world. Level 3 is in fact so large, they mostly do business by selling connectivity to their network to other ISPs that actually deal with consumers, instead of dealing with end users themselves. The IP addresses for Level 3's public DNS servers are 4.2.2.1 through 4.2.2.6. These IPs are easy to remember, but they've always been shrouded in a bit of a mystery. While they've been available for use by the public for almost 20 years now, it's not a service Level 3 officially has ever acknowledged or advertised. Why? We might never know. It's one of the great mysteries of our ancient sysadmin lore. Anyway, other easy to remember options are the IPs for Google's public DNS. Google operates public name servers on the IPs 8.8.8.8 and 8.8.4.4. Unlike the Level 3 IPs, these are officially acknowledged and documented by Google to be used for free by anyone. Most public DNS servers are available globally through Anycast. Lots of other organizations also provide public DNS servers, but few are as easy to remember as those two options. Always do your research before configuring any of your devices to use that type of name server. Hijacking outbound DNS requests with faulty responses is an easy way to redirect your users to malicious sites. Always make sure the name server is run by a reputable company, and try to use the name servers provided by your ISP outside of troubleshooting scenarios. Most public DNS servers also respond to ICMP echo requests, so they're a great choice for testing general internet connectivity using ping. Refresher time. Remember that DNS is a global system managed in a tiered hierarchy with ICANN at the top level. Domain names need to be globally unique for a global system like this to work. You can't just have anyone decide to use any domain name. It'd be chaos. Enter the idea of a registrar, an organization responsible for assigning individual domain names to other organizations or individuals. Originally, there were only a few registrars. The most notable was a company named Network Solutions, Inc. It was responsible for the registration of almost all domains that weren't country-specific. As the popularity of the internet grew, there was eventually enough market demand for competition in this space. Finally, the United States government and Network Solutions, Inc. came to an agreement to let other companies also sell domain names. Today, there are hundreds of companies like this all over the world. Registering a domain name for use is pretty simple. Basically, you create an account with the registrar, use their web UI to search for a domain name to determine if it's still available, then you agree upon a price to pay and the length of your registration. Once you own the domain name, you can either have the registrar's name servers act as the authoritative name servers for the domain, or you can configure your own servers to be authoritative. Domain names can also be transferred by one party to another, and from one registrar to another. The way this usually works is that the recipient registrar will generate a unique string of characters to prove that you own the domain and that you're allowed to transfer it to someone else. You'd configure your DNS settings to contain this string in a specific record, usually a text record. Once this information has propagated, it can be confirmed that you both own the domain and approve its transfer. After that, ownership would move to the new owner or registrar. An important part of domain name registration is that these registrations only exist for a fixed amount of time. You typically pay to register domain names for a certain number of years. It's important to keep on top of when your domain names might expire, because once they do, they're up for grabs and anyone else could register them. Long before DNS was an established and globally available technology, it was clear to computer operators that they needed a language-based system to refer to network devices. We've talked about how humans are way better at remembering descriptive words than numbers, but numbers represent the natural way that computers think and communicate. The original way that numbered network addresses were correlated with words was through host files. A host file is a flat file that contains on each line a network address followed by the host name it can be referred to as. For example, a line in a host file might read 1.2.3.4 web server. This means that on the computer where this host file resides, a user could just refer to web server instead of the IP 1.2.3.4. Hosts files are evaluated by the networking stack of the operating system itself. That means the presence of an entry there would translate to anywhere you might refer to a networking address. Sticking with our earlier example, a user could type web server into a web browser URL bar, or could issue a ping web server command, and it would get translated to 1.2.3.4 in either case. Host files might be ancient technology, but they've stuck around all this time. All modern operating systems, including those that power our phone and tablets, still have hosts files. One reason is because of a special IP address we haven't covered yet, the loopback address. A loopback address always points to itself. So, a loopback address is a way of sending network traffic to yourself. Sending traffic to a loopback address bypasses all network infrastructure itself, and traffic like that never leaves the node. The loopback IP for IPv4 is 127.0.0.1, and it's still, to this day, configured on every modern operating system through an entry in a hosts file. Almost every hosts file in existence will, in the very least, contain a line that reads 127.0.0.1 localhost, most likely followed by : 1 localhost, where : 1 is the loopback address for IPv6. Since DNS is everywhere, host files aren't used much anymore. But they still exist, and they're still important to know about. Some software even requires specific entries in the host file to operate properly, as antiquated as this practice may seem. Finally, host files are a popular way for computer viruses to disrupt and redirect users' traffic. It's not a great idea to use host files today, but they do have some useful troubleshooting purposes that can be helpful in IT support. Host files are examined before a DNS resolution attempt occurs on just about every major operating system. This lets you force an individual computer to think a certain domain name always points at a specific IP. Got it? We've covered a lot, so take time to go back if you need to, and make sure you understand the concepts we're discussing. Next up, a short quiz. You've probably been hearing people talk about the cloud more and more. There are public clouds and private clouds and hybrid clouds and rain clouds, but those aren't really relevant here. There are cloud clients and cloud storage and cloud servers too. You might hear the cloud mentioned in newspaper headlines and TV advertisements. The cloud is the future, so we're told, and IT support specialists really need to keep up on the latest innovations in tech in order to support them. But what exactly is the cloud? The truth is, the cloud isn't a single technology or invention or anything tangible at all. It's just a concept, and to throw in another cloud joke, a pretty nebulous one at that. The fact that the term the cloud has been applied to something so difficult to define is pretty fitting. Basically, cloud computing is a technological approach where computing resources are provisioned in a shareable way so that lots of users get what they need, when they need it. It's an approach that leans heavily on the idea that companies provide services for each other using these shared resources. At the heart of cloud computing is a technology known as hardware virtualization. Hardware virtualization is a core concept of how cloud computing technologies work. It allows the concept of a physical machine and a logical machine to be abstracted away from each other. With virtualization, a single physical machine called a host could run many individual virtual instances called guests. An operating system expects to be able to communicate with the underlying hardware in certain ways. Hardware virtualization platforms employ what's called a hypervisor. A hypervisor is a piece of software that runs and manages virtual machines, while also offering these guests a virtual operating platform that's indistinguishable from actual hardware. With virtualization, a single physical computer can act as the host for many independent virtual instances. They each run their own independent operating system, and in many ways are indistinguishable from the same operating systems running on physical hardware. The cloud takes this concept one step further. If you build a huge cluster of interconnected machines that can all function as hosts for lots of virtual guests, you've got a system that lets you share resources among all of those instances. Let's try explaining this in a more practical way. Let's say you have the need for 4 servers. First, you need an email server. You've carefully analyzed things and expect this machine will need 8 gigs of RAM to function properly. Next, you need a name server. The name server barely needs any resources since it doesn't have to perform anything really computational. But you can't run it on the same physical machine as your email server, since your email server needs to run on Windows and your name server needs to run on Linux. Now, the smallest server configuration your hardware vendor sells is a machine with 8 gigabytes of RAM, so you have to buy another one with those specifications. Finally, you have a financial database. This database is normally pretty quiet and doesn't need too many resources during normal operations. But for your end-of-month billing processes to complete in a timely manner, you determine the machine would need 32 gigabytes of RAM. It has to run on a special version of Linux designed just for the database, so the name server can't also run on this machine. So you order a server with that much RAM, and then a second with the same specifications to act as a backup. In order to run your business this way, you have to purchase 4 machines with a grand total of 80 gigabytes of RAM. That seems pretty outrageous since it's likely that only 40 gigabytes of this total RAM will ever be used at one time. Most of the month, you're using much less. That's a lot of money spent on resources you're either never going to use or rarely use. So let's forget about that model. Instead, let's imagine a huge collection of interconnected servers that can host virtualized servers. These virtual instances running on this collection of servers can be given access to the underlying RAM as they need it. Under this model, the company that runs the collection of servers can charge you to host virtual instances of your servers instead of you buying the 4 physical machines. And it could cost much less than what you'd spend on the 4 physical servers. The benefits of the cloud are obvious. But let's take it a step further. The cloud computing company that can host your virtualized instances also offer dozens of other services. So instead of worrying about setting up your own backup solution, you can just employ theirs. It's easy. And if you need a load balancer, you can just use their solution. Plus, if any underlying hardware breaks, they just move your virtual instance to another machine without you even noticing. To top it all off, since these are all virtual servers and services, you don't have to wait for the physical hardware you ordered to show up. You just need to click a few buttons in a web browser. That's a pretty good deal. In our analogy, we used an example of what a public cloud is, a large cluster of machines run by another company. A private cloud takes the same concepts, but instead it's entirely used by a single large corporation and generally physically hosted on its own premises. Another term you might run into, a hybrid cloud, isn't really a separate concept. It's just a term used to describe situations where companies might run things like their most sensitive proprietary technologies on a private cloud, while entrusting their less sensitive servers to a public cloud. Those are the basics of what the cloud is. It's a new model in computing where large clusters of machines let us use the total resources available in a better way. The cloud lets you provision a new server in a matter of moments and leverage lots of existing services instead of having to build your own. To sum up, It's blue skies ahead for anyone using the cloud. Sorry, I couldn't resist. Time for some real talk. Here's the hard truth. The IANA is out of IP addresses. When IPv4 was first developed, a 32-bit number was chosen to represent the address for a node on a network. The internet was in its infancy, and no one really expected it to explode in popularity the way it has. 32 bits were chosen, but it's just not enough space for the number of internet-connected devices we have in the world. IPv6 was developed exactly because of this issue. By the mid-1990s, it was more and more obvious that we were going to run out of IPv4 address space at some point. So a new internet protocol was developed, Internet Protocol version 6, or IPv6. You might wonder what happened to version 5, or IPv5. It's actually a fun bit of trivia. IPv5 was an experimental protocol that introduced the concept of connections. It never really saw wide adoption, and connection state was handled better later on by the transport layer and TCP. Even though IPv5 is mostly a relic of history, when development of IPv6 started, the consensus was to not reuse the IPv5 name. The biggest difference between IPv4 and IPv6 is the number of bits reserved for an address. While IPv4 addresses are 32 bits, meaning there can be around 4.2 billion individual addresses, IPv6 addresses are 128 bits in size. This size difference is staggering once you do the math. Don't worry, we won't make you. 2 to the power of 128 would produce a 39-digit long number. That number range has a name you've probably never even heard of, an undecillion. An undecillion isn't a number you hear a lot because it's ginormous. There really aren't things that exist at that scale. Some guesses on the total number of atoms that make up the entire planet Earth and every single thing on it get into that number range. That should tell you we're talking about a very, very large number. If we can give every atom on Earth its own IP address, we'll probably be okay when it comes to network devices for a very long time. Just for fun, let's look at what that number actually looks like. It looks like this. Whoa, mind-blowing, right? Just like how an IPv4 address is really just a 32-bit binary number, IPv6 addresses are really just 128-bit binary numbers. IPv4 addresses are written out in 4 octets of decimal numbers just to make them a little more readable for humans. But trying to do the same for an IPv6 address just wouldn't work. Instead, IPv6 addresses are usually written out as 8 groups of 16 bits each. Each one of these groups is further made up of 4 hexadecimal numbers. A full IPv6 address might look something like this. That's still way too long, so IPv6 has a notation method that lets us break that down even more. A way to show how many IPv6 addresses there are is by looking at our example IP. Every single IPv6 address that begins with 2001:0DB8 has been reserved for documentation and education, or for books and courses just like this one. That's over 18 quintillion addresses, much larger than the entire IPv4 address space, reserved just for this purpose. There are 2 rules when it comes to shortening an IPv6 address. The first is that you can remove any leading zeros from a group. The second is that any number of consecutive groups composed of just zeros can be replaced with 2 colons. I should call out that this can only happen once for any specific address. Otherwise, you couldn't know exactly how many zeros were replaced by the double colons. For this IP, we could apply the first rule and remove all leading zeros from each group. This would leave us with this. Once we apply the second rule, which is to replace consecutive sections containing just zeros with 2 colons, we'll end up with this. This still isn't as readable as an IPv4 address, but it's a good system that helps reduce the length a little bit. We can see this approach taken to the extreme with IPv6 loopback address. You might remember that with IPv4, this address is 127.0.0.1. With IPv6, the loopback address is 31 zeros with a 1 at the end, which can be condensed all the way down to just : 1. The IPv6 address space has several other reserved address ranges besides just the one reserved for documentation purposes, or the loopback address. For example, any address that begins with FF00: is used for multicast, which is a way of addressing groups of hosts all at once. It's also good to know that addresses beginning with FE80: are used for link local unicast. Link local unicast addresses allow for local network segment communications and are configured based upon a host's MAC address. The link local address are used by an IPv6 host to receive their network configuration, which is a lot like how DHCP works. The host's MAC address is run through an algorithm to turn it from a 48-bit number into a unique 64-bit number. It's then inserted into the address's host ID. The IPv6 address space is so huge, there was never any need to think about splitting it up into address classes like we used to do with IPv4. From the very beginning, an IPv6 address had a very simple line between network ID and host ID. The first 64 bits of any IPv6 address is the network ID, and the second 64 bits of any IPv6 address is the host ID. This means that any given IPv6 network has space for over 9 quintillion hosts. Still, sometimes network engineers might want to split up their network for administrative purposes. IPv6 subnetting uses the same CIDR notation that you're already familiar with. This is used to define a subnet mask against the network ID portion of an IPv6 address. When IPv6 was being developed, they took the time to introduce a few improvements instead of just figuring out a way to increase the address size. This should come as a relief to you, and IT support specialists love networks that perform well. One of the most elegant improvements was made to the IPv6 header, which is much simpler than the IPv4 one. The first field in an IPv6 header is the version field. This is a 4-bit field that defines what version of IP is in use. You might remember that an IPv4 header begins with this exact same field. The next field is called the traffic class field. This is an 8-bit field that defines the type of traffic contained within the IP datagram and allows for different classes of traffic to receive different priorities. The next field is the flow label field. This is a 20-bit field that's used in conjunction with the traffic class field for routers to make decisions about the quality of service level for a specific datagram. Next, you have the payload length field. This is a 16-bit field that defines how long the data payload section of the datagram is. Then you have the next header field. This is a unique concept to IPv6 and needs a little extra explanation. IPv6 addresses are 4 times as long as IPv4 addresses. That means they have more ones and zeros, which means that they take longer to transmit across a link. To help reduce the problems with additional data that IPv6 addresses impose on the network, the IPv6 header was built to be as short as possible. One way to do that is to take all of the optional fields and abstract them away from the IPv6 header itself. The next header field defines what kind of header is immediately after this current one. These additional headers are optional, so they're not required for a complete IPv6 datagram. Each of these additional optional headers contain a next header field and allow for a chain of headers to be formed if there's a lot of optional configuration. Next, we have what's called the hop limit field. This is an 8-bit field that's identical in purpose to the TTL field in an IPv4 header. Finally, we have the source and destination address fields, which are each 128 bits. If the next header field specified another header, it would follow at this time. If not, a data payload the same length as specified in the payload length field would follow. It's just not possible for the entire internet and all connected networks to switch to IPv6 all at once. There would be way too much coordination at play. Too many old devices that might not even know how to speak IPv6 at all, still requiring connections. So the only way IPv6 will ever take hold is to develop a way for IPv6 and IPv4 traffic to coexist at the same time. This would let individual organizations make the transition when they can. One example of how this can work is with what's known as IPv4 mapped address space. The IPv6 specifications have set aside a number of addresses that can be directly correlated to an IPv4 address. Any IPv6 address that begins with 80 zeros and is then followed by 16 ones is understood to be part of the IPv4 mapped address space. The remaining 32 bits of the IPv6 address is just the same 32 bits of the IPv4 address it's meant to represent. This gives us a way for IPv4 traffic to travel over an IPv6 network. But probably more important is for IPv6 traffic to have a way to travel over IPv4 networks. It's easier for an individual organization to make the move to IPv6 than it is for the networks at the core of the internet to. So while IPv6 adoption becomes more widespread, it'll need a way to travel over the old IPv4 remnants of the internet backbone. The primary way this is achieved today is through IPv6 tunnels. IPv6 tunnels are conceptually pretty simple. They consist of IPv6 tunnel servers on either end of a connection. These IPv6 tunnel servers take incoming IPv6 traffic and encapsulate it within traditional IPv4 datagrams. This is then delivered across the IPv4 internet space, where it's received by another IPv6 tunnel server. That server performs the de-encapsulation and passes the IPv6 traffic further along the network. Along with IPv6 tunnel technologies, the concept of an IPv6 tunnel broker has also emerged. These are companies that provide IPv6 tunneling endpoints for you, so you don't have to introduce additional equipment to your network. There are a lot of competing protocols to be used for these kinds of IPv6 tunnels. Since this is still a new and evolving space, it's not clear who the winner will be. I've left you with some links to read about the main competitors right after this video. It doesn't really matter which tunneling technology ends up becoming the most common solution. It'll probably fade away in time itself. The future of networking is the adoption of IPv6 as the main protocol at the network layer. And one day, we won't need any tunnels at all. The future is limitless and tunnelless, or something like that. You've done an amazing job getting through all this information. So take some time to pat yourself on the back. You've got one final quiz and a final project to get through, and then you can check this course off your to-do list. Are you starting to see the light at the end of the tunnel? You did it! You should be really proud of yourself, because getting through all of this material is a huge accomplishment. The material we've covered has been pretty technical and super complicated, and getting through it all is a real feat. Take a moment to think about just how much you've learned. You now know a lot about how computers communicate with each other, which is an essential part of how people communicate with each other. Computer networks are used by billions of people every day, and they form the backbone of the global economy. You've learned about how signals are carried across cables and how many different protocols are used in conjunction to make sure this data is delivered properly. You've learned about all sorts of network services like DNS that help humans use computers. This is all very important to learn. You'll be able to apply all of this knowledge into your IT support career. You can also just use it to help your own home network run better. Either way, congrats. You've given yourself a leg up. Next time you visit a social media site or stream a video or even just chat with your friends and family online, take a moment to think about how amazing it is that so many different network devices and layers and protocols are involved with every little bit of data sent across the internet. And you should also take a moment to marvel at the fact that you now understand how all of that works. Congratulations! In the next course, Operating Systems and You, Becoming a Power User, my friend and colleague Cindy Quach will be your guide as you navigate the Windows and Linux OSs. Get ready to have some fun and get your hands dirty as Cindy teaches you how to become a command line wizard.